Picture something that sounds impossible at first. A planet so ancient that it formed when our entire galaxy was still young, billions of years before Earth even existed. Scientists once thought this was impossible. They believed planets needed multiple generations of stars to create the heavy elements required for world building. That the universe has a way of surprising us, proving our assumptions wrong time and again. Reality is far stranger and more wonderful than our early models suggested. We'll explore this fascinating topic in depth in this video and discover just how ancient some worlds truly are. If you like these videos, I would appreciate if you clicked like or subscribed, as it's important for the channel and it helps others find it too, just like you did. Thank you. Now, let's get started. The Milky Way galaxy stretches across billions of light years, holding within it countless worlds we've never seen. Each planet tells a story written in cosmic time, measured not in human years, but in eons that dwarf our entire existence. When we look up at the night sky, we're glimpsing just the tiniest fraction of what's really out there. Our galaxy formed over 13 billion years ago, back when the universe itself was still relatively young. In those early epochs, the first generation of stars began to shine, lived their entire lives, and died in spectacular explosions. These stellar deaths weren't endings, but beginnings. They scattered heavier elements throughout space, the very building blocks needed to create rocky planets. The oldest planets in our galaxy likely formed during this ancient era, when the Milky Way was a very different place. Stars were closer together, and the chemistry of space was simpler. Yet even in that primordial environment, gravity was already at work, pulling together dust and gas into the first planetary systems. Think about what this means for a moment. Somewhere out there, orbiting a star we'll probably never see, there might exist a world that's older than our entire solar system. This ancient planet would have formed when Earth was nothing more than scattered particles drifting in an unborn stellar nursery. Such a world would have witnessed the birth and death of countless generations of stars. It would have seen massive stellar explosions that briefly outshone entire galaxies. Gravitational waves from colliding black holes would have rippled past it like cosmic tsunamis, stretching and compressing space itself in ways too subtle for any inhabitant to notice. The surface of this ancient world tells a story written in craters and geological formations. Every impact scar represents a moment in deep time, a collision with some wandering asteroid or comet. The rock layers beneath its surface contain chemical signatures from epochs when the galaxy's star formation rate was completely different from today. Scientists estimate that the oldest planets in our galaxy could be over 12 billion years old. That's nearly 3 times the age of Earth. When our sun was just beginning to condense from a cloud of gas and dust, these ancient worlds were already middle-aged, their surfaces shaped by billions of years of cosmic weather. The implications become even more fascinating when we consider the possibility of life. If life can emerge and evolve over geological timescales, then these ancient worlds have had an almost incomprehensible head start. While Earth's most complex life forms were still single-celled organisms, hypothetical life on these old planets might have had billions of additional years to develop and spread. Of course, age alone doesn't guarantee that life would flourish. A planet needs the right conditions, the right chemistry, the right distance from its star. It needs liquid water, a stable atmosphere, protection from harmful radiation. Many factors have to align just right, and they have to stay aligned for enormous periods of time, but the sheer number of ancient worlds increases the odds. Our galaxy contains hundreds of billions of stars, and we now know that planets are incredibly common. Even if only a tiny fraction of these worlds can support life, and only a tiny fraction of those actually develop it, the numbers still become staggering when multiplied across billions of years and countless star systems. The oldest planets also serve as natural laboratories for understanding planetary evolution. Their surfaces and atmospheres have been shaped by processes operating over timescales that dwarf anything we can observe directly. They've experienced climate changes that lasted longer than complex life has existed on Earth. These ancient worlds have orbited their stars through countless galactic seasons. Our entire solar system completes one orbit around a galaxy every 225 million years. The oldest planets have made this cosmic journey dozens of times, traveling through different regions of space, experiencing varying levels of cosmic radiation and stellar encounters. Some of these elder worlds might orbit stars that are themselves incredibly old and stable. Red dwarf stars can burn steadily for trillions of years, far longer than the current age of the universe. A planet orbiting such a star could potentially remain habitable for time periods that make Earth's entire future seem brief by comparison. The search for these ancient worlds requires looking in the oldest regions of our galaxy. The galactic halo contains some of the most primitive stars, formed from the nearly pristine hydrogen and helium left over from the Big Bang. The thick disk of the galaxy also harbors old stellar populations that might host planets from the early epochs of cosmic history. Finding and studying these worlds pushes the boundaries of our technology. They're often orbiting faint, distant stars, making detection extremely challenging. When we do spot them, they appear as the tiniest variations in starlight, subtle signals that require years of careful observation to confirm. Each discovery adds another piece to our understanding of how planetary systems form and evolve. These ancient worlds are like cosmic fossils, preserving information about conditions that existed when our galaxy was fundamentally different. They help us understand not just where we came from, but where we might be going in the vast sweep of cosmic time. The oldest planet in the Milky Way represents more than just an astronomical curiosity. It's a reminder that our perspective on time, shaped by human lifespans and historical records, captures only the briefest moment in a much grander story. Somewhere in the darkness between stars, ancient worlds continue their patient orbits, carrying within their rocks and atmospheres the accumulated wisdom of billions of years. When we think about age, we usually picture things in human terms. A century seems long, maybe even ancient to us. But out there in space, there are planets that make our entire civilization look like it happened yesterday. These worlds were already billions of years old when Earth was nothing more than cosmic dust, floating around, waiting to become something. The question of what makes a planet old isn't as straightforward as you might think. Age becomes this relative concept when you're dealing with cosmic scales. A mountain feels ancient compared to a tree, sure. A continent feels ancient compared to a mountain. But when astronomers talk about old planets, they're really talking about the age of the entire star system, where that planet formed. Picture this process for a moment. A star gets born, and around it there's this swirling disk of gas and dust. Tiny grains start bumping into each other, sticking together. Slowly, very slowly, they build up into bigger chunks. Those chunks become what scientists call planetesimals. Then those grow into protoplanets. Eventually, if everything goes right, you get full planets orbiting around their star. But here's where things get really interesting. For the longest time, scientists weren't sure if planets could even form in the early universe. The first stars that ever existed, they were made from the simplest stuff. Just hydrogen and helium, the basic elements that came from the Big Bang. All the heavier elements, the carbon, oxygen, silicon, iron, the materials that rocky planets like Earth are built from, those had to be created later. Stars are basically cosmic factories. They take simple elements and forge them into more complex ones. But here's the catch. Stars have to die for those elements to get released back into space. The first generation of stars lived fast, burned bright, and died young. They exploded as supernovas, scattering all those newly created heavy elements throughout the galaxy. Then new stars formed from that enriched material. Those stars lived and died too, adding even more elements to the cosmic mix. Generation after generation, the raw ingredients for planet building slowly accumulated in space. It's almost like cosmic baking, where you can't make the cake until you have all the ingredients. The early universe only had the basic stuff. Everything else had to be manufactured first, so naturally. Astronomers figured that planets must be relatively recent additions to the cosmic story. But the universe loves to surprise us. As our telescopes got better and our detection methods improved, we started finding planets in the most unexpected places. Some were orbiting incredibly old stars, stars that formed when our galaxy was still young and wild. This discovery suggested something remarkable. Planet formation might have started much earlier than anyone thought possible. Some of the oldest known planets formed billions of years before our own solar system even existed. Think about that for a second. There are worlds out there that were already ancient when our sun was just getting started, while the cloud of gas that would eventually become our solar system was still drifting through interstellar space, unformed and undecided. These ancient planets had already completed countless orbits around their stars. They had already experienced billions of years of cosmic weather, stellar radiation, and who knows what else. It's a profoundly humbling thought when you really sit with it. We measure our lives in decades. Our recorded history spans maybe a few thousand years. The entire story of human civilization, everything we've ever built, thought or dreamed, occupies just the thinnest possible slice of cosmic time. Meanwhile, these ancient worlds continue their silent dance through the darkness. They orbit their stars with the patience of eons, having witnessed cosmic events we can barely imagine. Some of them might have been around to see the galaxy take its current shape. They've survived stellar flares, asteroid impacts, and the slow evolution of their parent stars. The fact that planets could form so early tells us something profound about the universe's creativity. Even with limited ingredients, even in those early chaotic times when the galaxy was still figuring itself out, the cosmic machinery of planet formation was already at work. Dust was clumping, gravity was pulling, and worlds were being born in the darkness of space. These discoveries force us to reconsider our place in the cosmic timeline. Earth feels ancient to us, but it's actually a relatively young planet in galactic terms. Our solar system formed from material that had already been recycled through multiple generations of stars. We're made from cosmic hand, downs. If you think about it, finding planets around other stars presents one of astronomy's greatest puzzles. These distant worlds remain hidden, tiny and dark against the overwhelming brightness of their parent stars. For decades, astronomers could only guess at their existence. The breakthrough came with clever detective work. Scientists learned to watch for the subtle dance between star and planet. When a massive planet orbits a star, it doesn't simply circle around a fixed point. Both objects actually wobble around their shared center of gravity. This creates a gentle pull back and forth that shifts the star's light in measurable ways. The radial velocity method was born from this insight. Another technique emerged from patient observation. Sometimes, purely by chance, a planet's orbit carries it directly between us and its star. During these transits, the planet blocks a tiny fraction of starlight, creating a brief, barely perceptible dimming. It's like watching a moth cross in front of a distant streetlight. These methods have revealed thousands of exoplanets scattered throughout our galaxy. The diversity is staggering. Gas giants dwarf even Jupiter in size. Rocky worlds smaller than Earth drift through space. Some planets race around their stars in mere days, baked by intense radiation. Others follow distant, lonely paths that take centuries to complete. Among these discoveries lie planets of extraordinary age. Their host stars burn with the light of ancient suns, formed when the universe was young. By studying stellar properties, composition, temperature, and brightness, astronomers can estimate when these systems first ignited. Age becomes a cosmic fingerprint. The galaxy's oldest stars cluster together in dense, spherical groups, called globular clusters. These stellar cities orbit our galaxy's center like ancient monuments. Their stars formed over 10 billion years ago, perhaps 12 billion, when the Milky Way itself was barely recognizable. Picture the night sky from a world within such a cluster. Instead of scattered points of light, separated by darkness, thousands of brilliant stars would crowd the heavens. The sky would glow with perpetual twilight. True night might never fall, It would be a realm of endless starlight, beautiful and strange. In one of these ancient clusters, astronomers discovered something remarkable. A planet so old, it defies our understanding of planetary formation. This world existed when the universe contained fewer heavy elements, fewer of the building blocks we thought planets needed. Yet, there it orbits, patient and enduring. The timescales involved stretch the imagination. Our Milky Way has been creating stars for over 13 billion years. Our Sun, despite feeling eternal to us, formed relatively recently in this cosmic timeline. Earth arrived as something of a latecomer to the universal story. Somewhere out there, planets may have existed twice as long as our own world. What might such ancient worlds look like today? Perhaps their surfaces have been worn smooth by countless impacts over the eons. Maybe asteroids and comets have ground their mountains into gentle hills. Their atmospheres might have changed dramatically, multiple times. Early thick blankets of gas could have escaped to space, replaced by thinner veils, then perhaps thickened again through volcanic outgassing or comet impacts. The very air of these worlds tells stories spanning billions of years. The parent stars themselves evolve and change. Young stars burn hot and variable. As they age, they settle into steadier rhythms, but even then they gradually brighten over millions of millennia. An ancient planet has witnessed its sun's entire life story, from violent youth to steady middle age. Planets transform over such vast timescales. Mountain ranges rise through tectonic forces, then erode grain by grain until they become plains. Oceans might fill great basins, persist for billions of years, then slowly evaporate as their star brightens. The magnetic fields that protect these worlds strengthen and weaken in cycles we're only beginning to understand. Yet through all this change, one thing often remains constant. The orbital dance continues, steady and reliable. A planet's path around its star can persist for billions of years with almost clockwork precision. This stability seems miraculous when you consider all the chaos that could disrupt it. Passing stars might disturb the system. Asteroid impacts could alter a planet's rotation. The star itself changes mass over time, but somehow that fundamental rhythm endures. Orbit after orbit, year after year, the planet traces its path through space. There's something profound about this persistence. While everything else changes, the basic relationship between world and sun remains. It suggests that beneath all the surface drama of planetary evolution, deeper patterns govern the cosmos. Time may transform everything, but it does so within frameworks that themselves endure. The universe operates on timescales that humble human comprehension. We measure our lives in decades, our civilizations in millennia. But planets measure their existence in billions of years, patient travelers on journeys that span nearly the entire history of the cosmos itself. When we think about age in our daily lives, the concept seems straightforward enough. A person might live 80 years, a tree might stand for centuries, an ancient building might endure for millennia. These timescales feel manageable to our minds, even if they stretch beyond our personal experience. But when astronomers talk about the age of planets, they're operating in a realm where our usual understanding of time begins to break down completely. The universe itself has been around for roughly 13.8 billion years. That's a number so large it becomes almost abstract, like trying to count every grain of sand on every beach on Earth. Our own planet formed about 4.5 billion years ago, which means Earth has witnessed roughly 1/3 of all cosmic history. Yet even Earth is relatively young compared to some of the worlds that exist out there in the vast darkness of space. Stars form from collapsing clouds of gas and dust, and planets typically emerge from the leftover material swirling around these newborn suns. This means that most planets are roughly the same age as their host stars, give or take a few million years, but not all stars formed at the same time. The earliest stars began shining when the universe was still in its infancy, and some of those ancient stellar systems managed to create planets that have survived until today. Finding these ancient worlds requires detective work on a cosmic scale. Astronomers can't simply travel to a distant planet and examine rock samples to determine its age. Instead, they study the star that the planet orbits. Stars change in predictable ways as they age, much like how a burning candle gradually consumes its wax. The brightness shifts, the chemical composition evolves, the internal nuclear processes alter the star's structure over millions of centuries. By measuring a star's temperature, luminosity, and chemical fingerprint, scientists can estimate when that star first began to shine. If they find planets orbiting such a star, they can reasonably assume those worlds formed around the same time. It's like dating an ancient artifact by examining the archaeological layer where it was discovered. The oldest confirmed planet we know about orbits a star that formed when the universe was only about 1 billion years old. This world has been circling its sun for over 12 billion years, making it nearly 3 times older than our entire solar system. To put that in perspective, if Earth's 4.5 billion year history were compressed into a single day, this ancient planet would have existed for almost 3 full days before our world even began to form. Think about what that means for a moment. This planet was already ancient when the Milky Way galaxy was still relatively young. It existed before our sun gathered enough material to begin nuclear fusion. It was there, silently orbiting its star, billions of years before the first simple life forms appeared in Earth's primordial oceans. The sheer continuity of its existence across such vast stretches of time feels almost incomprehensible. Of course, survival over such immense timescales is far from guaranteed. Planets face countless dangers throughout their existence. Asteroid impacts can shatter worlds completely. Gravitational interactions with passing stars can fling planets out of their orbits entirely. Some planets gradually spiral inward toward their parent stars, eventually falling into the stellar furnace that once gave them warmth and light. The fact that any planet can survive for 12 billion years represents a kind of cosmic endurance test. This ancient world has weathered whatever catastrophes the universe could throw at it, maintaining its orbital path through countless stellar generations. It has witnessed the birth and death of other stars, the formation of new planetary systems, the gradual evolution of the galaxy itself. Stars don't remain stationary in space. They wander through the galaxy over millions of years, sometimes approaching other stellar systems, sometimes drifting into isolation. This ancient planet has traveled an unimaginable distance during its 12 billion year journey. Carried along by its star, has both moved through the slowly rotating spiral arms of the Milky Way. The chemical composition of such old planets likely differs significantly from younger worlds like Earth. When the universe was young, it contained mostly hydrogen and helium, the simplest elements created during the Big Bang. Heavier elements like carbon, oxygen, silicon, and iron. The building blocks of rocky planets were much rarer back then. These elements only became abundant after generations of stars had lived, died, and scattered their nuclear ashes into space. This means that the oldest planets probably formed from material that was relatively poor in heavy elements compared to the cosmic soup that created our solar system. They might have different internal structures, different atmospheric compositions, different geological processes. In a sense, they represent snapshots of planetary formation from a completely different era in cosmic history. The discovery of such ancient worlds forces us to reconsider our assumptions about planetary systems and their longevity. We used to think that planets were relatively short-lived on cosmic timescales, but finding worlds that predate our solar system by billions of years suggests that stable planetary systems can persist for most of the universe's entire history. This has profound implications for our understanding of where life might emerge in the cosmos. If planets can remain stable for 12 billion years or more, that provides an enormous amount of time for biological processes to develop and evolve. Life on Earth took roughly 4 billion years to progress from simple microbes to complex multicellular organisms. An ancient planet would have had 3 times that duration to develop whatever forms of complexity might be possible. The existence of such old planets also reminds us that our solar system, despite feeling eternal from our human perspective, is actually a relative newcomer to the galactic neighborhood. We're part of a second or third generation of planetary systems, built from the recycled remains of earlier stars and worlds that lived and died long before our sun even existed. The universe holds worlds that have witnessed eons we can barely imagine. Some planets drift through space in regions flooded with deadly radiation, their surfaces scorched by energies that would sterilize entire star systems. Others face the chaos of gravitational encounters, cosmic billiard games, where massive objects reshape orbits, sometimes flinging entire worlds into the cold darkness between stars. Yet, amid all this violence, countless planets maintain their steady dance around their stars. They circle year after year, century after century, millennium after millennium. There's something deeply comforting about that image, the thought of worlds persisting through time spans that dwarf human comprehension. These planets continue their orbital ballet while civilizations rise and crumble, while species emerge and vanish, while continents drift across their surfaces like slow dreams. When we talk about planetary age, though, we're really talking about comparison. Old compared to what, exactly? Earth itself stretches back over 4.5 billion years, already ancient by any human measure. So when astronomers discover a planet twice Earth's age, we're not just looking at something old, we're glimpsing a relic from an entirely different chapter of cosmic history. Picture the Milky Way as it existed when these ancient worlds first formed. The galaxy's spiral arms were less pronounced, more chaotic. Stars that pepper our night sky today simply didn't exist yet. The very chemistry of space was different back then. Heavy elements, the building blocks of rocky planets, were far scarcer because fewer generations of stars had completed their life cycles. Stars are the universe's alchemists. In their cores, they forge elements heavier than hydrogen and helium, silicon, iron, oxygen, magnesium, all the materials that eventually become rocky worlds, like Earth. When these stellar furnaces finally exhaust their fuel and explode as supernovas, they scatter these precious elements into space. Early in galactic history, this process had only just begun. That chemical scarcity shaped what kinds of planets could form. Rocky worlds were harder to assemble when the raw materials were so rare. Gas giants, however, could still gather easily from the abundant hydrogen and helium floating everywhere. This means the oldest planetary systems might look quite different from our own solar system, dominated by massive gaseous worlds rather than the rocky terrestrial planets we know. Studying these ancient worlds becomes a form of galactic archaeology. Each discovery tells us something about how chemistry evolved across cosmic time, how the availability of planet-building materials shifted as generation after generation of stars lived, died, and enriched the galaxy with heavier elements. There's something philosophically intriguing about planetary age that goes beyond mere numbers. We measure age as years, but what does billions of years actually mean to a planet? These worlds don't experience time the way we do. They don't remember their formation, don't anticipate their future. They simply exist, undergoing slow physical transformations, cooling gradually, shifting internally, wearing down through erosion, maintaining their orbits. For a planet, time isn't something noticed or felt. It's just the backdrop against which change happens. Yet for us, contemplating such vast temporal scales can be oddly soothing. It provides perspective on our daily struggles. Even our worst days, our most pressing concerns, seem smaller when placed against the quiet endurance of worlds that have persisted for billions of years. Astronomy offers this gift regularly, not solutions to our problems, but a reminder of the immense context in which those problems exist. It's a form of cosmic mindfulness, grounding us in something larger than our immediate experience. The search for the oldest planets faces practical limitations, though. Our instruments can only detect what they're capable of seeing. Distance, size, and the brightness of host stars all affect whether we can spot these ancient worlds. Many older planets likely remain hidden simply because they orbit faint stars in distant regions of the galaxy, beyond the reach of our current technology. This is why astronomers are careful to speak of the oldest known planet. Not simply the oldest planet, That word known carries weight, acknowledging the boundaries of our current understanding, admitting that the universe holds secrets we haven't yet uncovered. Somewhere in the Milky Way, there are almost certainly planets older than any we've discovered, worlds that formed when the galaxy was even younger, even more chemically primitive. They orbit ancient red dwarf stars in the galactic halo, or circle through the thick stellar populations near the galactic center, unnoticed by our telescopes. This possibility adds another layer of wonder to our cosmic perspective. The universe extends not just across incredible distances, but through incredible spans of time. Our exploration of both dimensions has barely begun. Each new discovery reminds us how much we don't yet know, how many stories remain hidden in the darkness between stars. These ancient worlds have witnessed the galaxy's entire adolescence and maturity. They've seen stellar nurseries bloom and fade, watched as the Milky Way's spiral structure crystallized into its current form, observed the gradual enrichment of interstellar space with the heavy elements that would eventually allow worlds like Earth to form. In a sense, the oldest planets are living libraries, their geology and atmospheric chemistry preserving records of cosmic conditions from the universe's earlier eras. Every measurement we make of these distant worlds teaches us something about how planetary systems evolve, how chemistry progresses on galactic scales, and how the cosmos itself has changed over time. When we consider how old things can get in our universe, we need to think about the lifespans of stars themselves. Stars don't live forever, as permanent as they might seem from our perspective. They go through birth, a long middle age, and eventually, they die. Some stars grow enormous as they age, becoming what we call red giants, slowly puffing away their outer layers into space. Others meet more violent ends, exploding as supernovas that can outshine entire galaxies. What's left behind depends on how massive the star was to begin with. Sometimes you get a white dwarf, a hot, dense ember about the size of Earth. Sometimes you get a neutron star where matter gets compressed so tightly that a teaspoon would weigh as much as a mountain. And sometimes you get a black hole where gravity becomes so strong that not even light can escape. Now imagine being a planet orbiting one of these aging stars. Your climate would change dramatically as your sun grows brighter or dimmer over millions of years. The star might lose mass, changing your orbit entirely. You might get pulled closer or drift farther away. In some remarkable cases, planets actually survive the death of their stars, continuing to orbit whatever remnant gets left behind, like cosmic survivors in a transformed world. To really understand how the most ancient planets in our galaxy came to exist, we need to slow down and think about how any planet forms in the first place. It's not a quick process, not dramatic in the way we might imagine cosmic events to be. Planet formation is, above all, an exercise in cosmic patience. Everything starts with a cloud, not the kind of cloud you see drifting overhead on a summer day, but an enormous cold cloud of gas and dust floating between the stars. These molecular clouds can stretch for dozens, even hundreds of light years across. They're made mostly of hydrogen, with some helium mixed in, plus tiny amounts of heavier elements, carbon, oxygen, silicon, iron, all scattered throughout microscopic grains of dust. These clouds aren't smooth and uniform. Some regions are denser than others, and sometimes something comes along to disturb the quiet. A nearby star might explode, sending shock waves rippling through the cloud. Two clouds might bump into each other. Or gravity might just start pulling the denser regions inward, slowly at first. Once gravity gets involved, it's hard to stop the process. A section of the cloud begins to collapse, gathering material as it shrinks, and because even the tiniest rotation gets amplified, as things get smaller, the cloud starts spinning faster and faster, like a figure skater, pulling their arms in tight. At the center of this spinning, collapsing cloud, matter piles up into what will eventually become a star. Around it, the remaining gas and dust flatten out into a rotating disk, what astronomers call a protoplanetary disk. This is where planets are born. In the beginning, the disk is full of tiny particles, dust grains smaller than sand. They drift around, bump into each other, and sometimes stick together. At these small scales, static electricity can make grains cling to each other, forming slightly larger clumps. Those clumps collide with others, and very gradually, they grow. This early stage is surprisingly fragile. Collisions have to be gentle enough for particles to stick, rather than just bounce off or shatter. Turbulence in the disk can help bring particles together, but it can also tear them apart. Gravity matters, but when things are still tiny, other forces are just as important. Over vast stretches of time, grains become pebbles. Pebbles gather into bigger chunks. Eventually, objects large enough for gravity to really take charge begin to form. These are called planetesimals, and they can be anywhere from a few kilometers to hundreds of kilometers across. Once these planetesimals exist, things start happening faster. Gravity lets them pull in additional material more efficiently. They collide with each other, sometimes merging together, sometimes breaking apart, but gradually building up larger and larger objects. Given enough time, some of these bodies become protoplanets, worlds in the making. This stage can get pretty chaotic. Protoplanets might slam into each other in enormous impacts that reshape entire worlds. Our own moon probably formed when something about the size of Mars crashed into the young Earth, blasting debris into orbit that eventually clumped together. But not every planetary system goes through such violence. Some planets might form in more orderly ways, slowly accumulating material over millions upon millions of years. The whole process can take anywhere from a few million to tens of millions of years after the star forms. That sounds like an eternity from our human perspective, but astronomically speaking, it's actually pretty quick. The recipe for planet formation needs three main ingredients: gas, dust, and time. Dust provides the raw material for rocky planets like Earth. Gas allows giant planets to form, especially if a solid core gets massive enough to grab huge envelopes of hydrogen and helium before the disk disappears. And time, vast amounts of time, allows all the collisions and gravitational interactions to slowly shape the system into its final form. There's something almost philosophical about this process. How the universe takes its time to build worlds. Nothing about planet formation is rushed. It's a reminder that on cosmic scales, patience isn't just a virtue, it's a fundamental requirement for creating the complex, beautiful systems we see around other stars today. Looking up at the night sky, we might imagine that every star went through the same process to get its family of planets. But the reality is far more complex, and honestly, far more interesting. Not every spinning disk of dust and gas around a young star actually manages to create planets at all. Some of these disks, they just fade away before anything substantial can form. The material gets blown away by stellar winds, or it simply disperses into space, leaving the star alone. Other disks might only manage to create tiny rocky worlds, barely larger than asteroids. And then there are disks that produce nothing but massive gas giants, worlds made almost entirely of hydrogen and helium. Each planetary system that does form gets shaped by its starting conditions. The mass of the original disk matters enormously. So does the temperature, which depends on how close the star is to other bright stars. The chemical makeup of the disk plays a huge role too, and if there are other stars nearby, their gravitational pull can mess with the whole process in unpredictable ways. This is why the planets we've found orbiting other stars are so wonderfully strange. There are hot Jupiters, massive gas giants, that their atmospheres are literally boiling away. These worlds complete an orbit in just a few days, racing around their stars at incredible speeds. Then we have super-Earths, rocky planets that are bigger than our home world but smaller than Neptune. Some of these might have thick atmospheres, others might be bare rock. We really don't know what standing on one would be like. Perhaps most fascinating are the planets that orbit binary star systems. Imagine looking up at a sky lit by two suns, watching double shadows move across alien landscapes. These worlds experience complex seasons as their stars dance around each other in glaciation. Planet formation isn't like following a recipe. It's more like jazz, a theme with countless variations. Each system improvises based on what materials are available and what forces are at play. When we think about the very oldest planets in our galaxy, we have to consider something crucial. Early in the Milky Way's history, heavy elements were much rarer than they are today. The first generations of stars were made almost entirely of hydrogen and helium. When these stars died, they scattered heavier elements into space, but it took time for these materials to become abundant. This scarcity of heavy elements meant that the dust needed to build rocky planets was hard to come by. In those ancient times, creating large rocky worlds like Earth would have been much more challenging. Gas giants, which rely mainly on hydrogen and helium, might have been the norm instead. This leads to a fascinating possibility. Some of the oldest planets in our galaxy, worlds that formed over 10 billion years ago, might not look anything like Earth. They could be gas giants orbiting close to their stars, or icy worlds in the outer reaches of their systems, or planets circling stars very different from our Sun. There's another wrinkle in planetary formation that makes things even more interesting. Planets don't always stay where they originally formed. They can migrate, drifting inward toward their star or outward into the cold depths of their system. This happens because of interactions with the disk of material that's still swirling around the young star. The gravitational dance between the planet and this disk can cause the planet to spiral inward, sometimes dramatically. This is probably how those hot Jupiters ended up so close to their stars. They likely formed much farther out, then migrated inward over millions of years. Gravitational encounters between planets can also shuffle orbits like cards in a deck. Sometimes these interactions are gentle, just nudging a world into a slightly different path. Other times they're violent, flinging planets into highly elliptical orbits, or even ejecting them from their systems entirely. These ejected worlds become rogue planets, lonely wanderers drifting through interstellar space without a star to call home. They're cold, dark places, lit only by the faint glow of distant stars. Yet they're out there, possibly in huge numbers, invisible nomads traveling between the stars. Over billions of years, planetary systems continue to evolve and change. Orbits that seemed stable can become chaotic. Planets can crash into each other in spectacular collisions that reshape entire worlds. Sometimes these collisions happen long after the planets first formed, adding new chapters to their geological stories. But despite all this potential chaos, many planetary systems do settle into long-term stability. Planets find stable orbits and stick to them for billions of years. Some even get locked into resonances, where their orbital periods form simple mathematical ratios. This creates a kind of gravitational harmony, with planets moving in synchronized patterns around their star. This stability is what allows truly ancient planets to exist today. Worlds that have been orbiting their stars since the early days of the galaxy, witnessing cosmic history unfold around them. One of the most remarkable discoveries in modern astronomy is that planet formation isn't rare at all. When we look at young stars, we see protoplanetary disks everywhere. These spinning disks of dust and gas seem to be a natural part of how stars form. Most stars, perhaps nearly all of them, probably have planets of some kind. This realization has completely changed how we think about our galaxy. Planets aren't exotic rarities scattered here and there. They're a normal, expected outcome of star formation, which means that as soon as the Milky Way had enough heavy elements to work with, planets started appearing everywhere. Some of those early worlds are probably still out there, orbiting ancient red dwarf stars that will outlive our Sun by trillions of years. These planets are silent witnesses to the long story of our galaxy, repositories of history stretching back to when the universe was young. The environment where stars form also plays a crucial role in determining what kinds of planets they end up with. Stars are often born in clusters, nurseries where hundreds or thousands of stars form close together. In these crowded neighborhoods, massive hot stars pump out intense radiation that can strip away protoplanetary disks from smaller stars nearby. Close encounters between stars can also disrupt the delicate process of planet formation. A star passing too close can gravitationally scatter the material in a disk, preventing planets from growing large enough to become stable worlds. But in quieter regions of space, away from these stellar nurseries, protoplanetary disks can persist much longer. This gives planets more time to grow, potentially leading to more diverse and complex planetary systems. When astronomers study very old stars, they pay close attention to their chemical composition. Stars with very low concentrations of heavy elements are typically ancient, formed when the galaxy was young and these elements were scarce. Finding planets around such stars tells us that world building was possible even under these challenging conditions. This has been one of the genuine surprises in astronomy. Planets seem more adaptable and resourceful than we once thought. The universe found ways to construct worlds even when the raw materials were in short supply. There's something deeply comforting in this idea. Given enough time, basic ingredients, and the patient work of gravity, complexity emerges almost inevitably. Tiny grains of dust stick together to form pebbles. Pebbles grow into boulders. Boulders become asteroids. And asteroids, under the right conditions, can grow into entire worlds. These worlds can then persist for enormous spans of time, stable platforms where the slow work of chemistry and perhaps even biology can unfold. It's a reminder that patience, more than anything else, might be the universe's greatest creative force. The story of planets begins long before Earth ever existed, back when the galaxy was essentially a cosmic wasteland for world building. Picture the universe in its infancy, just after the Big Bang swept through everything. The chemical makeup was almost laughably simple compared to what we see today. Nearly everything was hydrogen with some helium thrown in, and just the tiniest whisper of lithium. That was it, really. No carbon, no oxygen, no silicon, no iron. None of the building blocks we think of as essential for making solid worlds. This chemical simplicity created a fascinating paradox. Stars were forming, sure, but the planets we might expect to orbit them simply couldn't exist yet. The raw materials weren't there. It's like trying to bake a cake when all you have is flour. No eggs, no sugar, no butter. The universe was missing its planetary ingredients entirely. Those first stars, the ones astronomers call population 3 stars, were born from this basic hydrogen and helium mix. Without heavier elements around to help cool down the collapsing gas clouds, these ancient stars grew to incredible sizes. We're talking about stellar giants, sometimes 50 times more massive than our Sun, sometimes even 100 times bigger. They were cosmic behemoths, burning through their furious pace. The trade-off for all that mass and brightness was a tragically short lifespan. These stellar giants would shine intensely for maybe just a few million years before running out of fuel completely. Then came the fireworks, spectacular explosions called supernovas that could outshine entire galaxies for weeks. But here's where things get philosophically interesting. Those explosions weren't just endings, they were beginnings in disguise. Inside those massive stars, nuclear fusion had been quietly cooking up heavier elements. Carbon, oxygen, silicon, iron, all the ingredients for rocky worlds were being forged in stellar cores under unimaginable pressure and heat. When the stars exploded, they scattered these newly created elements into space, mixing them with the surrounding gas like cosmic seasoning. Over millions of years, this enriched material would become part of the next generation of stars. This process, this gradual buildup of heavier elements, represents one of the most profound changes in galactic history. Astronomers have a peculiar habit of calling all elements heavier than helium metals, even things like oxygen and carbon that we definitely wouldn't consider metals in everyday life. It's just convenient scientific shorthand, but it points to something deeper about how we categorize the universe. This metallicity, as it's called, turns out to be absolutely crucial for planet formation. Those tiny dust grains that serve as the seeds of future worlds, they're made from these heavier elements. Without enough metals floating around, there simply isn't enough solid material to build rocky planets. Even gas giants need solid cores to get started. So low metallicity affects everything. In those earliest epochs of the Milky Way, When metallicity was still incredibly low, planet formation faced serious challenges. Not impossible challenges, mind you, but the process was far less efficient, far less common than it would become later. This explains why truly ancient planets are such rare finds today. The cosmic conditions they needed simply weren't abundant until several generations of stars had already lived out their entire life cycles. But there's another complication to consider. Those early star-forming regions weren't just chemically different, they were much more violent and chaotic places. Picture dense clusters packed with massive stars, all crowding together in ways that would seem almost claustrophobic by today's galactic standards. These massive stars didn't just shine brightly, they produced intense radiation and powerful stellar winds that could completely strip away the protoplanetary disks around nearby younger stars. Imagine trying to build something delicate while someone nearby keeps setting off fireworks. The raw material you need keeps getting blown away before it has time to settle and accumulate properly. That's essentially what was happening to potential planet-forming disks in these early crowded stellar nurseries. The environment was simply too turbulent for the slow, patient process of planetary assembly. As the galaxy aged and evolved, things gradually became more hospitable. Star-forming regions spread out and became less dense. The proportion of massive stars decreased, giving smaller, gentler stars more room to develop their planetary systems in peace. It's almost like the galaxy was learning how to create planets more effectively over time. Meanwhile, the chemical enrichment process continued relentlessly. Each stellar generation contributed more heavy elements to the interstellar medium, slowly but steadily increasing the galaxy's metallicity. By the time stars like our Sun began forming, billions of years later, the Milky Way had accumulated a rich chemical inventory. This abundance explains why our solar system contains such a diverse array of elements, why Earth has that iron core, those silicate rocks, and all that life-giving oxygen. Of course, some stars did manage to form during those intermediate periods, when metallicity was low but not negligible. Around these stars, planets could indeed form, though they might have quite different compositions and structures compared to the worlds we're familiar with today. Finding and studying these ancient stellar systems gives astronomers a window into planetary formation under very different cosmic conditions. Many of the galaxy's oldest stars today reside in globular clusters, those spectacular spherical swarms of hundreds of thousands of stars, all bound together by gravity. These clusters represent some of the earliest stellar communities in the Milky Way, cosmic time capsules preserving stars that formed when the galaxy itself was still young and chemically simple. The oldest parts of our galaxy hold secrets that stretch back to when the universe was still young and wild. Globular clusters, these ancient collections of stars, contain some of the most remarkable neighborhoods in space. Picture hundreds of thousands of stars, all crammed together in a space that's only a few dozen light-years wide. These clusters have been around for 10, sometimes 12 billion years, making them older than most things we can imagine. If you could somehow stand on a planet inside one of these clusters, the night sky would be completely overwhelming. Instead of seeing a few thousand stars like we do from Earth, you'd see countless brilliant points of light filling every corner of darkness. Many of these stars would shine far brighter than anything in our own sky. The whole experience would be like living inside a cosmic chandelier. But this crowded stellar neighborhood comes with serious drawbacks. Stars in globular clusters are packed so tightly that they constantly bump into each other. Gravitationally speaking, these close encounters can completely wreck planetary systems, throwing planets out of their orbits or even flinging them into deep space entirely. It's like trying to maintain a delicate garden while earthquakes keep shaking the ground. This makes it particularly amazing when astronomers do find planets in globular clusters. These worlds didn't just manage to form in such chaotic conditions. They've stayed stable for billions upon billions of years. They're cosmic survivors in the truest sense, having weathered countless stellar storms and gravitational upheavals. Early planet formation tells us another fascinating story through stars with very low metallicity. In astronomy, metals mean any element heavier than hydrogen and helium, the basic building blocks that planets need. Scientists once thought that stars with very few of these heavier elements couldn't possibly host planets. There simply wouldn't be enough raw material to build worlds. But the universe, it turns out, is far more creative than we gave it credit for. Astronomers have discovered planets orbiting these metal-poor stars, showing that cosmic construction projects can happen under conditions we thought were impossible. The universe seems to have a knack for finding ways to build worlds, even when the odds are stacked against it. However, the planets that formed in those early cosmic times were probably quite different from the ones we see today. Gas giants may have dominated the scene back then, since there wasn't much solid material available to construct large rocky planets. This doesn't mean rocky worlds were completely absent, just that they were likely much rarer. The early universe was biased towards building big, gaseous worlds rather than the smaller solid planets we're more familiar with. Time itself created another major challenge for early planet formation. The process of building planets takes millions of years, requiring patience on a cosmic scale. But the earliest stars burned through their fuel incredibly quickly, living only a few million years before exploding in spectacular supernovas. This created a race against time, where planetary systems had to form and stabilize before their host stars died violent deaths. Many early planetary systems probably lost this race. They were disrupted before planets could fully form or find stable orbits. Later generations of stars lived longer, more predictable lives, giving planets the time they needed to develop properly and settle into lasting patterns. When astronomers study the oldest known planets today, they often find these ancient worlds in very unusual circumstances. Some orbit neutron stars, those incredibly dense remnants left behind after massive stars explode. Others circle white dwarfs, the cooling embers of stars that have exhausted their nuclear fuel. At first glance, this seems completely impossible. How could any planet survive the death of its star, especially when that death involves one of the most violent explosions in the universe? The answer reveals just how resilient planetary systems can be. Some planets survive by being far enough away from their star when it explodes, riding out the cosmic storm at a safe distance. In other cases, planets actually form after the explosion, coalescing from material that falls back into orbit around the stellar remnant. These scenarios are incredibly complex, and scientists are still working to understand all the details. The rarity of very old planets isn't just about our ability to find them. It reflects the entire history of our galaxy, a story of gradual change and cosmic evolution. Early conditions made planet formation much more difficult, like trying to build a house during a perpetual storm. Many of the planetary systems that did manage to form were later disrupted by the dynamic, often dangerous environment of a young galaxy. The ancient planets that do exist today are survivors in every possible way. They formed when the odds were against them, in an era when the universe was less hospitable to world building. Then they endured for billions of years, weathering the slow transformation of the galaxy around them. There's something quietly humbling about contemplating that kind of endurance. These worlds have been following their orbital paths for spans of time so vast that entire generations of stars have been born and died in the same galaxy. The spiral arms of the Milky Way have shifted and reformed. Stars that were once neighbors have drifted apart, their relative positions completely rearranged by the galaxy's slow rotation. Through all of these cosmic changes, those ancient planets just kept orbiting, patient, persistent, following the same gravitational dance they've been performing since before our solar system even existed. They're like cosmic monks, maintaining their meditation through eons of galactic transformation. Stars have been revealing their secrets through light for centuries, and astronomers learned to read the chemical fingerprints hidden in starlight long before they started hunting for distant worlds. Every beam of light carries information about the element that created it, written in dark lines that appear when you spread the light into a rainbow spectrum. These spectral lines work like a cosmic barcode, telling us exactly which elements exist inside a star. Iron leaves its mark at specific wavelengths, carbon at others, oxygen at its own distinct positions. By studying these patterns, scientists discovered something unexpected. Not every star contains the same recipe of elements. Some stars burn bright with heavy elements mixed throughout their cores and atmospheres. Others consist almost entirely of the simplest materials, hydrogen and helium, with barely a trace of anything more complex. This difference might seem minor, but it shapes the entire story of planet formation across the galaxy. Astronomers call this difference metallicity, though their definition of metal stretches far beyond what you might expect. In their vocabulary, every element heavier than hydrogen and helium counts as a metal. Carbon becomes a metal, oxygen too, along with silicon, iron, nickel, and dozens of others. These so-called metals become the raw materials from which planets eventually form. Think of planet formation like construction work happening in space. The heavy elements determine how much building material gets delivered to the construction site. When a star forms surrounded by clouds rich in these heavier elements, tiny dust particles can stick together, clump up, and gradually build into larger and larger objects. But when a star forms in a region where heavy elements remain scarce, the construction project faces shortages. Fewer dust grains float around in the disk surrounding the young star. Less raw material means fewer opportunities for solid worlds to take shape. This explains a curious fact about our galaxy's history. Planets were much rarer billions of years ago, not because the physics worked differently, but because the ingredients simply weren't available yet. The very first stars contained almost no heavy elements at all, just the hydrogen and helium left over from the Big Bang. Those ancient stars lived fast and dramatic lives, fusing lighter elements into heavier ones deep in their cores. When they exploded as supernovas, they scattered these newly forged elements across space like cosmic seeds. Each generation of stars added more heavy elements to the galaxy's inventory, slowly enriching the raw materials available for the next round of star and planet formation. By the time our sun ignited, roughly 4.5 billion years ago, the galaxy had spent eons accumulating heavy elements. The cloud, that eventually became our solar system, contained enough carbon, silicon, iron, and other materials to build rocky worlds, asteroids and comets. Earth itself stands as proof of this cosmic enrichment process, with iron concentrated in its core, silicon and oxygen forming much of its rocky crust. If you could travel backward through time, you'd encounter stars whose composition tells the story of a much younger galaxy. These ancient objects contain less than 1% of the heavy elements found in our sun. They formed when the universe was still learning how to make the ingredients for solid worlds. Finding planets around such metal-poor stars presents both challenges and revelations. It's challenging because these worlds often appear smaller and dimmer than planets around metal-rich stars. But it's revealing because it shows that nature finds ways to build planets even when working with limited materials. The connection between stellar metallicity and planet formation became clear as astronomers discovered more and more exoplanets. Stars rich in heavy elements consistently showed up as hosts to giant planets, especially gas giants resembling Jupiter. The correlation appeared so strong that metallicity became a useful predictor for where to search for certain types of worlds. Gas giants depend heavily on metallicity because of how they form. The current model suggests these planets start as solid cores built from dust and rock. Once a core grows massive enough, it can gravitationally capture huge amounts of hydrogen and helium gas from the surrounding disk, inflating into a giant planet. Without sufficient heavy elements to build that initial solid core, the gas in the disk might disperse before the planet can capture it. Rocky planets also rely on metallicity, though perhaps more forgivingly. Even small, solid worlds need enough dust particles to gradually accumulate into planetesimals, then protoplanets, and finally full-fledged planets. When dust remains scarce, fewer rocky bodies form, and those that do manage to coalesce often stay relatively small. Yet the universe consistently surprises us with its creativity. Observations have revealed planets orbiting stars with lower metallicity than early models predicted possible. These discoveries suggest that planet formation operates across a broader range of conditions than scientists first imagined. This flexibility becomes especially important when considering very old stars, many of which formed when heavy elements were still rare. If high metallicity were absolutely required for planet formation, these ancient stars would almost never host worlds, but planets have been detected around some of these metal-poor stars, proving that the process can adapt to challenging circumstances. The specific types of heavy elements also matter, not just their total abundance. Different elements contribute different properties to the planet-forming process. Silicon and oxygen combine to form rocky minerals. Iron provides material for dense cores. Carbon enables complex chemistry that might eventually support life. This elemental diversity means that even stars with similar overall metallicity might produce different types of planetary systems, depending on which specific heavy elements dominate their composition. Some stars might be rich in silicon and poor in iron, leading to planets with different internal structures than worlds forming around iron-rich stars. The story of metallicity and planet formation connects to bigger questions about our place in the cosmic timeline. We live in an era when the galaxy has had billions of years to accumulate heavy elements, making Earth-like planets possible. Earlier in galactic history, such worlds might have been nearly impossible to form. This suggests something profound about the emergence of complexity in the universe. Life as we know it depends on heavy elements, the same materials that enable rocky planet formation. Both biological complexity and planetary diversity have increased as the galaxy aged and became more chemically enriched. The building blocks of worlds depend entirely on what materials are floating around when planets start to come together. Silicon, magnesium, and iron become the backbone of rocky materials, while carbon and oxygen team up to create molecules and various types of ice. It's fascinating to think that the exact recipe of elements determines what kind of world emerges from the cosmic dust. When carbon outnumbers oxygen in these planetary nurseries, something remarkable might happen. Scientists wonder about worlds where graphite or diamond could dominate the landscape instead of familiar silicate rocks. These carbon-rich planets remain largely theoretical, but the incredible variety of worlds we've discovered suggests that nature experiments with all sorts of compositions. The same elemental abundance that shapes planets also influences the smaller leftovers, asteroids and comets. These objects are like time capsules, preserving secrets about conditions that existed over 4 billion years ago. When we examine meteorites that fall to Earth, we're essentially reading a chemical diary from the solar system's infancy. The distant star systems astronomers play detective with starlight itself. The chemical signature of a star reveals the composition of the disk that once surrounded it, the same disk from which any planets would have formed. It's like reading the ingredients list for worlds we may never directly observe. The metal content of stars becomes a cosmic calendar of sorts. Ancient stars, born when our galaxy was still in its youth, typically contain fewer heavy elements. Any planets orbiting these stellar elders would be incredibly old themselves, witnesses to billions of years of galactic evolution. But age isn't always straightforward in space. Some regions of our galaxy have remained relatively poor in heavy elements even in recent times, so astronomers must combine multiple clues, studying how stars move and where they're located, to piece together their true ages. Globular clusters represent some of the most extreme environments where planets might exist. These dense collections of ancient stars formed early in our galaxy's history, with metal content far below what we find in our Sun. The crowded conditions make it incredibly difficult to spot planets, and the scarcity of heavy elements makes planet formation itself less likely. Yet remarkably, at least one planetary system has been discovered in such an environment. This finding proves that worlds can emerge, even when the cosmic pantry seems nearly bare, challenging our assumptions about what conditions are necessary for planet formation. Every heavy element that makes up our bodies tells a story of stellar death and rebirth. The iron flowing through your bloodstream, the calcium strengthening your bones, every atom was forged in the nuclear furnaces of stars that died long before our Sun was born. Planets are essentially the descendants of these stellar ancestors, assembled from the ashes of previous generations. The metal content of any star serves as a genealogical record, revealing how many cycles of stellar birth, life and death contributed to its formation. Our galaxy has grown progressively richer in heavy elements over billions of years, with newer stars generally containing more metals than their ancient predecessors. This gradual enrichment has profoundly influenced the types of planetary systems that can form. The likelihood of creating complex rocky worlds has increased dramatically as the galaxy has aged and accumulated more diverse building materials. The rarity of truly ancient planets becomes clear when we consider their extraordinary survival story. Not only did they form in environments where heavy elements were scarce, but they've also endured for billions of years while the galaxy itself continued evolving around them. Some of these cosmic veterans orbit small, long-lived stars that burn their nuclear fuel so slowly they can remain stable for tens of billions of years. Others circle stellar-ready completed dramatic evolutionary cycles. Into dish, the exotic remains of stars that have already completed dramatic evolutionary cycles. Finding these ancient worlds requires exceptional observational skill and sometimes considerable luck. The signals they produce are often incredibly faint, buried in the noise of cosmic background radiation and stellar activity. Each discovery represents a triumph of human ingenuity and technological advancement. The study of planetary metallicity ultimately connects us to the grand narrative of cosmic evolution. Every world is a product of its time and place in galactic history, shaped by the specific blend of elements available when it formed. Understanding this relationship helps us appreciate both the commonalities and the remarkable diversity of planetary systems throughout the universe. When we look up at the night sky, we're essentially peering into a cosmic history book. Every point of light carries stories from billions of years ago, and some of those stories involve planets that existed long before our Earth even began to form. The universe has been creating worlds for an incredibly long time, much longer than we might imagine. Think about how challenging it would be to spot a firefly next to a massive searchlight from several miles away. That's basically what astronomers face when they try to find planets around other stars. These distant worlds don't produce their own light, like stars do. They simply reflect a tiny fraction of the starlight that hits them. The contrast is so extreme that direct observation becomes nearly impossible in most cases. Instead of seeing planets directly, scientists have become masters of detective work. They watch for the subtle ways that planets reveal their presence through their effects on nearby stars. It's like trying to figure out if someone is dancing in a room by watching the shadows on the wall, rather than seeing the dancer themselves. One of the most elegant methods involves listening to the cosmic waltz between stars and planets. When we think of planetary orbits, we often imagine a massive star sitting perfectly still while a tiny planet circles around it. But that's not quite accurate. Both the star and planet actually dance around their shared center of gravity. The star's dance moves are much smaller because it's so much more massive, but they're still there, a gentle wobble back and forth. This stellar wobble creates something beautiful in the realm of physics. As the star moves slightly toward us, then away from us, the light it emits gets stretched and compressed like sound from a passing ambulance. When the star approaches, its light shifts toward the blue end of the spectrum. When it moves away, the light becomes slightly redder. These color shifts are incredibly tiny, but modern instruments can measure them with remarkable precision. The story gets even more interesting when a planet happens to pass directly between its star and Earth. During these cosmic alignments, called transits, the planet blocks a small amount of starlight for a few hours. The star appears to dim slightly, then return to its normal brightness. By measuring how much the star dims and how long the dimming lasts, astronomers can figure out both the size of the planet and how long it takes to complete one orbit. Space telescopes have turned this transit method into a planetary discovery machine, finding thousands of worlds by patiently watching for these tiny dips in starlight. Each discovery adds another piece to our understanding of how common planets really are throughout the galaxy. But finding a planet is just the beginning when you're searching for truly ancient worlds. The real challenge lies in figuring out when these distant solar systems first formed. Unlike rocks on Earth, which can be dated using radioactive decay, planets orbiting other stars don't come with convenient timestamps. Stars, however, are like cosmic clocks that tick in slow motion over billions of years. As they age, they change in predictable ways that astronomers can measure and model. Young stars burn hot and bright, while older stars gradually evolve through different phases of their lives. By studying a star's temperature, brightness, and chemical composition, scientists can estimate how long it has been shining. The chemical fingerprints of stars tell particularly fascinating stories about cosmic history. Early in the universe's development, only hydrogen and helium existed in significant quantities. Heavier elements like iron, carbon, and oxygen had to be forged inside stars and scattered through space when those stars died. This means that stars with fewer heavy elements likely formed earlier in cosmic history, when the galaxy was still relatively young and chemically simple. Stellar motion provides another clue to age. The oldest stars in our galaxy often travel in elongated, tilted orbits that carry them far above and below the main disk of the Milky Way. These unusual paths suggest they formed during the galaxy's early, more chaotic period, before things settled into the relatively orderly spiral structure we see today. Sometimes astronomers get lucky and find planets in star clusters, where hundreds or thousands of stars all formed at roughly the same time from the same cloud of gas and dust. Dating the cluster gives a reliable age estimate for any planets discovered there. Globular clusters are particularly valuable in this regard, since many of them contain stars that are over 10 billion years old, making them among the most ancient objects in our galaxy. One of the most unusual planet hunting techniques involves some of the strangest objects in the universe. Pulsars are the collapsed remnants of massive stars that ended their lives in spectacular supernova explosions. These incredibly dense objects, no larger than a city but containing more mass than our Sun, spin rapidly while emitting beams of radio waves from their magnetic poles. As a pulsar rotates, its radio beams sweep across space like lighthouse beams, creating precisely timed pulses that astronomers can detect. Some pulsars are so regular that they rival the accuracy of atomic clocks. If a planet orbits such a pulsar, its gravitational pull causes tiny variations in the timing of these radio pulses. By measuring these variations with extraordinary precision, astronomers can detect planets that would be impossible to find any other way. The first confirmed planets beyond our solar system were actually discovered orbiting a pulsar, worlds unlike anything previously imagined. These planets orbit the remnant of a dead star, in an environment so harsh that any life as we know it would be impossible. Yet their discovery opened our eyes to the incredible diversity of planetary systems throughout the galaxy. Pulsar planets have also provided some of our best evidence for truly ancient worlds. Since pulsars themselves can be very old, and since they're often found in regions containing the galaxy's oldest stars, planets detected around them may represent some of the earliest worlds ever formed. Another technique that sounds like science fiction, but works in practice, involves using gravity itself as a telescope. Einstein's theory of general relativity tells us that massive objects bend space and time, which affects the path that light takes through the universe. When one star passes in front of another more distant star, the foreground star's gravity can act like a lens, temporarily magnifying the background star's light. If the foreground star has a planet, the planet's gravity adds its own small contribution to this lensing effect, creating a brief additional brightening that lasts just a few hours or days. These gravitational microlensing events are rare and unpredictable, but they can reveal planets at enormous distances, including ancient worlds in the central bulge of our galaxy. Each planet detection method has its own personality and limitations. Some techniques excel at finding massive planets close to their stars, while others can spot smaller worlds at greater distances. Some provide detailed information about planetary atmospheres, while others reveal only the most basic properties. By combining different approaches, astronomers have built an increasingly diverse catalogue of exoplanets. The process of confirming that a planet is truly ancient requires patience and careful analysis. Scientists must consider the age of the host star, the chemical composition of the system, the star's motion through space, and sometimes the age of surrounding stellar populations. These age estimates always come with uncertainties, sometimes spanning hundreds of millions of years or more. But when all the evidence points to an age of 10 or 12 billion years, the implications become profound. Such a planet must have formed when the universe was less than a quarter of its current age. When the Milky Way was still a young and evolving galaxy, the light we detect from such systems began its journey toward Earth, before our own solar system even existed. There's something deeply humbling about observing these ancient worlds. They serve as reminders that planetary formation has been occurring throughout most of cosmic history, while Earth and its fellow planets are relatively recent additions to the galactic family. Other worlds have been circling distant stars for eons, perhaps witnessing the formation and destruction of countless stellar generations. Studying ancient planetary systems also provides insights into the long-term evolution of worlds over billions of years. By comparing old systems with younger ones, astronomers can investigate how planetary orbits change over time, how atmospheres evolve, and how stellar radiation affects planets throughout their extended lifetimes. The search for ancient worlds continues to push the boundaries of astronomical technology. Next-generation telescopes, both on Earth and in space, promise to detect even fainter signals and more distant planets than ever before. These advanced instruments will expand our inventory of ancient worlds and help refine our understanding of when and how the first planets formed in our galaxy. As we develop better techniques for finding and studying these cosmic time capsules, we're not just learning about the past, we're also gaining insights into the future, including the ultimate fate of our own solar system over the vast spans of time that lie ahead. In this way, the ancient planets scattered throughout the galaxy serve as both historical documents and prophetic visions, connecting us to the deep time scales on which the universe operates. Around 12 billion years ago, when the universe was still in its cosmic infancy, a world began forming that would outlast most of what we see in the night sky today. This ancient planet, bearing the catalogue designation PSRB 26b, represents something almost beyond our usual conception of time. While dinosaurs lived and died on Earth, this distant world was already ancient beyond measure. The story of how we found this celestial time capsule begins in one of the most crowded neighborhoods in our galaxy. Globular clusters pack hundreds of thousands of stars into spaces that, astronomically speaking, are incredibly cramped. Imagine trying to fit every person in a major city into just a few city blocks, and you start to get a sense of how densely packed these stellar communities really are. In such crowded conditions, stars don't live the quiet, isolated lives that our sun enjoys. They bump into each other, steal each other's companions, and generally create the kind of gravitational chaos that most planets couldn't survive. For decades, astronomers assumed that worlds simply couldn't exist in these stellar mosh pits. The gravitational tugs and pulls would either tear planets apart or fling them into the cold depths of space. That assumption made the discovery in globular cluster Messier 4 all the more startling. About 5,600 light-years away, in the direction of the constellation Scorpius, something impossible was quietly orbiting through space. Not just a planet, but a planet with a story that would rewrite our understanding of how early worlds could form. At the heart of this discovery sits one of the universe's most extreme objects, a pulsar. These are the collapsed cores of massive stars, so dense that a sugar cube of their material would weigh as much as Mount Everest. When these neutron stars spin, they sweep beams of radiation across space, like cosmic lighthouses. Some pulsars are so precise in their rotation that they rival the best atomic clocks humans have ever built. This particular pulsar, spinning dozens of times each second, seemed to be keeping perfect time when astronomers first studied it. But as they listened more carefully to its radio heartbeat, something peculiar emerged. The timing wasn't quite as steady as it should be. Tiny variations in the pulse arrival times suggested that the pulsar wasn't sitting still in space, but was instead being tugged around by something else. That something turned out to be a white dwarf, the dense remnant of a star that had long ago burned through its nuclear fuel and shed its outer layers. Binary pairs like this aren't uncommon in the universe. Many pulsars have stellar companions that orbit them in a gravitational dance, but this system had another secret. Even after accounting for the white dwarf's gravitational influence, the pulsar's timing still showed mysterious variations. These subtle changes pointed to a third object, something much less massive than the white dwarf, but still substantial enough to affect the motion of both stellar remnants. That third object was a planet. The precision required to detect a world this way staggers the imagination. The planet's gravity creates tiny wobbles in the motion of its stellar hosts. Those wobbles, in turn, caused the pulsar's radio beams to arrive at Earth just microseconds earlier or later than expected. By measuring these incredibly small timing variations over years of observation, astronomers could map out the unseen planet's orbit and estimate its mass. What they found was a gas giant, roughly 2 to 3 times more massive than Jupiter, taking about 100 Earth years to complete each orbit around its unusual binary star system. The planet maintains a respectful distance from its hosts, orbiting at roughly the same distance that Uranus keeps from our Sun. But the real revelation came when astronomers calculated the age of this system. Because it resides in Messier 4, where stars formed more than 12 billion years ago, the planet must be nearly as ancient as the cluster itself. This world began taking shape when the universe was less than 2 billion years old, making it roughly 3 times older than our entire solar system. Consider what this means for a moment. When this ancient planet was forming, the Milky Way looked completely different. Most of the stars we see in our night sky didn't exist yet. The heavy elements that make up rocky worlds like Earth were still relatively rare, scattered thinly throughout the cosmos by only a few generations of stellar explosions. This scarcity of heavy elements challenged prevailing theories about planet formation. Many astronomers believed that worlds, especially large ones, needed relatively metal-rich environments to coalesce efficiently. Yet here was a massive planet that had formed when the universe was still impoverished in these building blocks of worlds. The discovery forced scientists to reconsider how early in cosmic history planets could appear. It suggested that world building could begin even when the raw materials were scarce, opening up the possibility that planets might be far more common throughout the universe's history than previously thought. The story of how this ancient world survived to the present day reads like an epic tale of cosmic endurance. The system that hosts it has experienced catastrophic changes over billions of years. One of the original stars exploded as a supernova, creating the pulsar that now serves as the planet's primary gravitational anchor. Another star evolved into a white dwarf, shedding vast amounts of material into space during its death throes. Through all of these dramatic events, somehow, the planet persisted. Supernova explosions can disrupt planetary orbits across vast distances. The complex gravitational interactions common in globular clusters regularly tear apart stellar systems and fling their components into new configurations. Yet this world weathered every cosmic storm. Some scenarios suggest the planet didn't originally form where we find it today. In the chaotic environment of a globular cluster, stars regularly exchange companions through gravitational interactions. The planet might have started life orbiting a completely different star, only to be traded between stellar systems like a cosmic bargaining chip until it ended up in its current unusual home. The dense stellar environment that nearly destroyed this world also helped preserve it in an unexpected way. The same gravitational interactions that can tear systems apart can also stabilize them in new configurations. The planet now orbits both stellar remnants, locked in a gravitational relationship that has apparently remained stable for billions of years. What strikes many astronomers about this discovery is how it expands our sense of possibility in the universe. Here is a world that has witnessed the cosmic dark ages, the formation of the first galaxies, and the slow chemical enrichment of the universe through countless stellar generations. It predates not just life on Earth, but Earth itself by an almost unimaginable span of time. In a sense, this ancient planet serves as a cosmic time capsule, carrying information about conditions in the very early universe. Its mere existence tells us that planet formation could begin much earlier in cosmic history than we once believed possible. It suggests that worlds might have been scattered throughout the universe long before our own solar system even began to form. The precision required to detect and study such a distant world also represents a triumph of human ingenuity. Using nothing more than the tiny timing variations in radio pulses, astronomers piece together the story of a planet that has been silently orbiting through space since the universe's youth. It's a reminder of how much we can learn about the cosmos simply by listening carefully to its subtle signals. When we consider the profound age of certain celestial bodies, we encounter timescales that stretch our understanding to its limits. Some planets have existed for 12 billion years, a duration that predates most of what we see in our night sky. This particular world formed when our galaxy was still assembling itself, long before our sun even existed. The environment surrounding such an ancient planet tells a story unlike anything in our solar neighborhood. Nestled within a globular cluster, this world experiences a sky filled with countless stars, packed far more densely than what we observe from Earth. True darkness becomes a rare phenomenon, when starlight streams from every direction, creating a perpetual celestial glow. Gas giants like this one lack the solid surfaces we associate with terrestrial worlds. Their atmospheres consist mainly of hydrogen and helium, with scattered traces of heavier elements mixed throughout. The absence of solid ground means these planets exist as swirling masses of gas, shaped by gravitational forces and atmospheric dynamics that operate on massive scales. Living near a pulsar creates conditions that challenge our typical understanding of planetary environments. These stellar remnants emit intense radiation beams, rather than the steady visible light we expect from ordinary stars. Pulsars themselves are remarkably compact, roughly the size of a city, yet they represent some of the densest objects in the universe. The radiation environment around such stellar objects can be extreme, though distance provides some protection for orbiting bodies. The pulsar's beams sweep across space, like a cosmic lighthouse, creating a rhythm that has persisted for billions of years. This regularity makes pulsars incredibly precise timekeepers, allowing astronomers to detect even the slightest gravitational influences from nearby planets. Contemplating the orbital mechanics of such systems reveals fascinating details about gravitational relationships. This ancient world completes one orbit roughly every century, meaning it has circled its stellar companions perhaps 100 million times since formation. Each revolution represents a journey through space that spans decades in human terms, yet constitutes merely a single cycle in the planet's endless dance. The formation timeline of this world places it among the earliest planetary systems in cosmic history. When it condensed from primordial material, many fundamental processes that shaped our galaxy were still unfolding. Star formation rates were different, heavy elements were less abundant, and the overall structure of galactic clusters was still evolving. Comparing this timeline to Earth's history provides perspective on the relative youth of our own world. Our planet's oldest rocks date back about 4 billion years, while the earliest evidence of life extends beyond 3 billion years. This ancient gas giant has existed 3 times longer than life has persisted on Earth, witnessing eras of cosmic evolution that preceded biological processes entirely. During its immense lifespan, this planet has observed the birth and death of countless stars. Stellar nurseries have formed, massive stars have exploded as supernovas, and white dwarfs have cooled gradually over billions of years. The gravitational environment has shifted as star clusters drifted through galactic space, yet the planet has maintained its orbital relationship with its pulsar companion. The discovery of such ancient worlds has fundamentally altered astronomical thinking about planetary formation and survival. These findings demonstrate that planets can emerge much earlier in cosmic history than previously assumed, and they can persist through extreme events that would destroy less stable systems. The diversity of planetary environments extends far beyond the relatively calm conditions of our solar system. Globular clusters present unique challenges for planetary formation and retention. These dense stellar communities experience frequent gravitational encounters that can disrupt planetary orbits or eject worlds entirely from their systems. The fact that planets can survive in such environments suggests robust formation mechanisms and stable orbital configurations. The survival of planets around pulsars also indicates remarkable resilience in planetary systems. Pulsars form through supernova explosions that release enormous amounts of energy and can completely sterilize surrounding space. Any planet that existed before the supernova would face intense radiation and gravitational disruption, Yet some worlds manage to survive or even form anew from the aftermath. These discoveries expand our understanding of where planets can exist and persist throughout cosmic time. Worlds can orbit stellar remnants, thrive in dense cluster environments, and maintain stability through gravitational events that reshape entire systems. The universe appears far more accommodating to planetary survival than early models suggested. Ancient planets serve as natural archives, preserving information about conditions that existed during the early epochs of galactic evolution. Their atmospheric compositions, orbital characteristics, and structural properties carry signatures of primordial processes that operated billions of years ago. Studying these worlds provides direct insight into how planetary systems formed under very different cosmic conditions. The chemical composition of such early planets likely differs significantly from worlds that formed later in galactic history. Heavy elements were much scarcer during the universe's youth, created only through successive generations of stellar fusion and supernova explosions. Planets forming from this primordial material would have contained different ratios of elements compared to more recent worlds. Atmospheric evolution over such extended timescales raises intriguing questions about planetary development. Gas giants can lose significant portions of their atmospheres to stellar radiation and solar winds over billions of years. The current state of these ancient atmospheres represents the result of countless interactions with their stellar environment across cosmic time. Internal planetary structure also evolves dramatically over such periods. Heat sources change as radioactive elements decay, gravitational settling redistributes materials, and external influences alter magnetic field generation. Understanding these long-term processes helps astronomers predict how planets evolve throughout their lifespans. The persistence of orbital stability over 12 billion years demonstrates the remarkable predictability of gravitational systems. Despite countless perturbations from passing stars, changing stellar masses, and evolving cluster dynamics, some planetary orbits maintain their basic characteristics across enormous timescales. This stability suggests that certain orbital configurations possess inherent resilience against disruption. As observational techniques improve and more planets are discovered around various types of stellar objects, astronomers continue refining models of planetary system evolution. Each new discovery adds pieces to the puzzle of how common ancient worlds might be throughout the galaxy. The universe may contain numerous examples of planets that formed during its earliest epochs. These findings remind us that planetary formation represents a continuous process throughout cosmic history, rather than a phenomenon limited to recent times. Worlds have been condensing from stellar material for most of the universe's existence, creating a vast population of planets with diverse ages, compositions, and evolutionary histories. The concept of deep time challenges human intuition about permanence and change. 12 billion years encompasses a duration so vast that it defies direct comprehension, yet this represents the actual lifespan of real worlds orbiting in space. Such timescales put human civilization into perspective as a brief moment within much larger cosmic narratives. When we look out into the cosmos, we find worlds that have been drifting through space for longer than our minds can really grasp. There's something humbling about discovering a planet that's been around for 12 billion years, when our own Earth feels ancient at just 4 billion. It's like finding a grandfather clock that's been ticking since before your neighborhood even existed. These incredibly old worlds teach us something profound about the nature of planetary systems. They show us that once gravity finds its rhythm, once orbits settle into their cosmic dance, they can keep spinning for almost unimaginable stretches of time. We might expect that after billions of years, something would go wrong, that gravitational tugs and stellar changes would eventually shake things apart. But here's the fascinating thing. Stability can persist on timescales that approach the age of the entire galaxy. Of course, not every planetary system enjoys such longevity. Over the eons, many planets do wander from their original paths. Some spiral inward toward their stars, others drift outward into the cold darkness. Some get ejected entirely after close encounters with passing objects, becoming lonely wanderers in interstellar space. But the very existence of these ancient survivors tells us that long-term stability isn't some rare cosmic accident. It's actually quite achievable when conditions align properly. What's particularly intriguing about these elderly planets is when they formed. A world that's 12 billion years old came into being when our galaxy was still in its youth, when the cosmic mixture was quite different from today. Back then, the heavier elements that we often think planets need, things like silicon and iron and carbon, were much scarcer than they are now. Stars had only had a few billion years to cook up these elements in their cores and scatter them through space when they died. This discovery reshapes how we think about planet formation entirely. It suggests that the threshold for building worlds is lower than we once believed. Planets didn't have to wait for the universe to become rich in heavy elements. They could start forming with whatever materials were available, even in those more primitive cosmic conditions. The implications ripple outward in fascinating ways. If planets could form early in galactic history, then planetary systems might have been present for most of the galaxy's lifetime. This means that the physical stages where complex chemistry could unfold, where interesting processes could begin, have existed far longer than we previously imagined. Whether life actually took advantage of these early opportunities remains an open question, one that keeps scientists awake at night with wonder. But just having planets present means the theaters existed, even if we don't know what plays might have been performed on those ancient stages. There's something poetic about imagining worlds where chemical evolution had billions of extra years to experiment, to try combinations and processes that younger planets never had time to explore. Age transforms planets in ways both subtle and dramatic. Over billions of years, worlds gradually surrender their internal heat to the cold emptiness of space. The warmth left over from their violent formation slowly leaks away. Radioactive elements buried in their cores provide some additional heating, but these cosmic furnaces burn lower as time passes, their fuel gradually exhausted through natural decay. For rocky worlds, this cooling brings profound changes. Tectonic activity, those grinding, shifting motions of crustal plates, may slow to a crawl or stop entirely. Volcanoes that once painted the sky with fire may fall silent. Magnetic fields, generated by the churning of molten material deep underground, can weaken and eventually vanish, leaving the planet naked to the harsh radiation of space. Gas giants follow their own aging process. These massive worlds start their lives relatively warm and puffy, inflated by their internal heat, but as eons pass, they radiate away this energy and slowly contract, becoming more compact and dense. A gas giant that formed 12 billion years ago might look remarkably different from a young one of similar mass, like comparing an elderly person to their childhood photograph. Atmospheres, too, bear the marks of time's passage. High-energy radiation from nearby stars can gradually strip away the lighter gases, molecule by molecule, especially if the planet orbits close to its host. Chemical reactions driven by starlight and cosmic radiation slowly alter the atmospheric cocktail, transforming the very air that shrouds these worlds. Over such vast periods, these processes can completely transform a planet's character and climate. A world that started with one kind of atmosphere might end up with something entirely different, shaped by billions of years of slow but relentless change. Perhaps most remarkably, these ancient planets reveal the incredible durability of planetary material itself. Rocks, metals, and frozen gases can persist in the cold vacuum of space for timeframes that dwarf human civilization. On active worlds like Earth, geological processes constantly reshape the surface, recycling old materials and erasing ancient features. But on quieter worlds, surfaces can preserve records of cosmic events for almost unthinkable spans of time. Our own moon gives us a glimpse of this preservation in action. Without atmosphere or active geology, its face still bears scars from impacts that occurred billions of years ago. Imagine then, a planet or moon that has remained geologically dormant for 10 or 12 billion years. Its surface could hold a record stretching back almost to the galaxy's youth, a cosmic library written in crater walls and ancient lava flows. These elderly worlds also illuminate the long dance between stars and planets. Stars change as they age, their brightness and temperature shifting over cosmic time. The story of how these changes affect their planetary companions unfolds over billions of years. Stars don't stay the same throughout their lifetimes, and this creates a fascinating puzzle for any planets that happen to orbit them. The energy they put out changes dramatically over billions of years, which means a planet's environment can shift in ways that are almost impossible to imagine. Think about it. A world that formed when its star was young and energetic might find itself in completely different conditions as that star ages and transforms. The Methuselah planet gives us one of the most extreme examples of planetary survival we've ever discovered. This ancient world has witnessed its host star go through an entire lifetime, transforming from a normal star into a white dwarf, which is basically a stellar corpse. But that wasn't the end of the drama, because there was another star in the system that took an even more violent path, collapsing down into a neutron star. The planet somehow managed to keep orbiting through all of this chaos. What's remarkable is that surviving these stellar deaths means the planet lived through events that should have destroyed it. When massive stars die, they explode as supernovas, releasing more energy in a few seconds than our Sun will produce in its entire 10 billion year lifetime. The fact that planets can survive such catastrophic events tells us something profound about the resilience of these cosmic systems. Globular clusters like Messier 4, where the Methuselah planet lives, are some of the oldest structures in our galaxy. These dense collections of stars have been orbiting around the center of the Milky Way for over 10 billion years. In such crowded neighborhoods, stars are constantly pulling on each other with their gravity, shifting orbits and reshaping entire systems. Yet somehow, planetary systems can maintain their stability, even in these chaotic environments. The age of this planet forces us to think about cosmic history in a completely different way. When this world first formed, the universe itself was only about 1 billion years old. That's a time period so remote that it challenges our ability to imagine it. Galaxies were still in the process of assembling themselves, and the very chemistry of the cosmos was different from what we see today. Heavy elements like iron and carbon, which are essential for building rocky planets, were much rarer back then. Most of these elements are created inside stars and scattered into space when those stars die. In the early universe, there simply hadn't been enough time for many generations of stars to live and die, so the raw materials for planet building were in short supply. If you could somehow travel back to that ancient era and stand on the surface of the Methuselah planet, the night sky would look completely alien. The Milky Way had a different structure, with star formation happening at a much faster rate than today. Many of the familiar stars and constellations we see now simply didn't exist yet. The entire cosmic environment was more violent and dynamic. This ancient planet serves as a kind of fossil record for astronomers studying how galaxies evolve. Its very existence places strict limits on our theories about how quickly heavy elements accumulated in the early universe and how rapidly the first planetary systems could form. Scientists have to make sure their models can account for the presence of such old worlds. There's something almost poetic about the way planets accumulate damage over such vast timescales. Every few million years, asteroids and comets slam into these worlds, gradually reshaping their surfaces and sometimes their internal structure. In the early solar system, these impacts happened much more frequently, creating what we call the late heavy bombardment period. An ancient planet like Methuselah has experienced billions of years of these collisions. Even events that are extremely rare can become commonplace when you have enough time. It's like watching erosion work on a mountain, except the timescales involved are so vast that entire mountain ranges could rise and fall multiple times. For gas giant planets, impacts don't leave permanent craters the way they do on rocky worlds, but they still have profound effects. They mix the atmosphere, potentially bringing material from deep inside the planet up to the surface layers. Over billions of years, this constant stirring can completely change the composition and appearance of these worlds. Our own solar system, at 4.5 billion years old, is practically middle-aged compared to the Methuselah planet. The Sun is expected to remain stable for several billion more years, though it will gradually brighten and eventually make Earth uninhabitable. After that, our star will swell into a red giant and shed its outer layers, leaving behind a white dwarf remnant. Some of the outer planets in our solar system might actually survive this transformation, continuing to orbit the white dwarf that remains. In that sense, the Methuselah planet offers us a glimpse into a possible far future for our own cosmic neighborhood. It's both sobering and oddly comforting to know that planetary systems can persist for such enormous spans of time. There's something deeply calming about contemplating these vast timescales. Human civilization, with all its urgency and drama, represents just a tiny fraction of cosmic history. The universe operates on its own schedule, unhurried by our daily concerns. Mountains rise and fall, species evolve and go extinct, and through it all, ancient worlds like Methuselah continue their patient orbits. These old planets aren't just curiosities from the distant past, they're part of our same galactic neighborhood. They orbit around the same central black hole that our solar system does, sharing the same cosmic environment even though they're separated from us by thousands of light years. In a very real sense, we're all connected by the same gravitational forces that hold our galaxy together. Each new discovery of an ancient planet adds another chapter to the story of how worlds form and evolve. Some planets get ejected from their systems during stellar death throes, wandering alone through interstellar space. Others get consumed by their expanding stars. But a few, like the remarkable Methuselah planet, manage to endure, serving as witnesses to the entire history of the cosmos. The way planets form, evolve, and persist through cosmic time brings us face to face with some truly ancient worlds. These planetary systems have been orbiting their stars for billions of years longer than Earth has even existed. When we think about where these old worlds are located, we find ourselves peering into some of the most crowded neighborhoods in our galaxy. Imagine looking up at a night sky where true darkness never arrives. Instead of seeing a few thousand scattered points of light, the entire sky glows with an overwhelming abundance of stars. Some of these stars shine so brilliantly that they actually cast shadows on the ground. You wouldn't be able to pick out familiar patterns or constellations because every direction you look, stars are packed together in dense formations. This is what the night sky looks like inside a globular cluster, those ancient stellar communities that represent some of the oldest structures in the Milky Way. Each globular cluster forms a nearly perfect sphere of stars, all held together by their mutual gravitational attraction. A single cluster might contain hundreds of thousands of stars, all crammed into a space that's only a few dozen light years across. To understand just how densely packed these regions are, consider that our nearest stellar neighbor, Proxima Centauri, sits more than 4 light years away from us. In the heart of a globular cluster, stars are often separated by distances that are just a fraction of that, sometimes less than 1/10 of a light year apart. This incredible closeness completely transforms the environment that planets experience. Here in our corner of the galaxy, the Sun and its family of planets drift through space in relative solitude. The nearest stars are so far away that their gravitational influence on our solar system is practically negligible. Over billions of years, a passing star might slightly disturb the outermost regions of our solar system, perhaps nudging some of the icy bodies that orbit far beyond Neptune. But the inner planets continue their orbits largely undisturbed. Inside a globular cluster, the story is completely different. Stars regularly pass much closer to each other, and over the vast spans of cosmic time, these close encounters can dramatically alter planetary systems. A planet's orbit might be stretched or compressed by the gravitational tug of a passing star. In some cases, planets can be pulled away from their original star entirely, either captured by a different star or ejected into the cold depths of interstellar space. For many years, astronomers thought that such chaotic environments would be far too unstable for planetary systems to survive. The logic seemed straightforward enough. If stars are constantly passing nearby, their gravitational influence would gradually tear apart the delicate orbital arrangements of planets. Given enough time, most planetary systems would simply fall apart. The discovery of planets within globular clusters has revealed that survival is indeed possible. Even under these crowded conditions, stability doesn't require perfect isolation from other stars. It only requires that close encounters remain rare enough or distant enough that the gravitational disturbances don't accumulate into catastrophic orbital changes. Many stars in globular clusters actually reside in the outer regions, where the stellar density is much lower than in the crowded central core. In these quieter neighborhoods, planetary systems can remain relatively undisturbed for long periods. Even in the denser regions, the time between close stellar encounters can still stretch across millions of years, providing plenty of time for planets to maintain stable orbits. The age difference between globular cluster stars and the stars in our region of the galaxy is striking. Most stars in these clusters formed at roughly the same time, more than 10 billion years ago. By stellar standards, they are incredibly ancient. Many of the more massive stars have already completed their entire life cycles, evolving into white dwarfs, neutron stars, or black holes. This means that planetary systems in globular clusters exist not only in crowded environments, but also in regions that have been evolving for an immense span of time. Stars have changed, died, and sometimes even swapped companions through complex gravitational interactions. The cluster itself has completed many orbits around the center of our galaxy, gradually losing some of its outer stars as tidal forces pull them away. Despite all this activity and change, the cluster remains gravitationally bound, forming a long-lived community of stars that travels through the galaxy as a single unit. The brightness of the night sky would be one of the most immediately noticeable features of life in such an environment. On Earth, the Milky Way appears as a faint ribbon of light that's only visible under the darkest skies. Inside a globular cluster, the combined light from thousands of nearby stars could create a state of constant twilight, depending on exactly where a planet is located within the cluster. Individual stars might appear larger and more brilliant than any star visible from Earth, simply because they would be so much closer. Having so many nearby stars also raises fascinating questions about temperature and radiation. While the combined light from distant stars wouldn't significantly warm a planet, stars that pass relatively close could influence the radiation environment over long time periods. A passing star might brighten the sky for thousands of years before gradually drifting away again. These encounters would unfold so slowly that they would be imperceptible within a single lifetime. But over millions of years, they could subtly alter the background brightness and character of the sky. The chemical composition of globular clusters sets them apart from younger regions of the galaxy in important ways. These clusters formed during an era when heavy elements were much less abundant throughout the universe. Their stars tend to have what astronomers call low metallicity, which affects the types of planets that can form around them. Rocky planets like Earth might be relatively uncommon in these environments, while gas giants might make up a larger fraction of the planets that do exist. Even so, the confirmed existence of planets in globular clusters demonstrates that planet formation wasn't entirely prevented by the scarcity of heavy elements. The universe found ways to construct worlds, even when working with limited raw materials. This adaptability speaks to the fundamental processes that drive planet formation, processes that are apparently robust enough to operate under a wide range of conditions. Any form of life that might exist in such a cluster would experience both time and space very differently than we do. Day and night would still be determined by the planet's rotation and its distance from its host star, but the broader environment would be far from empty. The concept of deep, starless darkness might be completely foreign. It's intriguing to consider how such a brilliantly illuminated sky might affect the development of astronomy for any observers living there. On Earth, the relative sparseness of bright stars in our night sky makes it easy to recognize patterns and group stars into constellations. In a globular cluster, the abundance of bright stars might make such pattern recognition much more challenging, or perhaps it would lead to entirely different ways of organizing and understanding the night sky. Living in the heart of a globular cluster would mean looking up at a sky filled with thousands, maybe tens of thousands of brilliant stars. The sheer density of these ancient stellar neighborhoods creates a nighttime panorama that's almost impossible for us to imagine. Individual constellations, the familiar patterns we trace in our own sky, would probably disappear into the overwhelming brightness of countless suns. The nearest stars in such a cluster would appear as blazing beacons, dominating entire sections of the heavens with their radiance. But here's something remarkable. Over the span of just a few centuries, you could actually watch some stars shift their positions in the sky. On Earth, stellar motion is so gradual that human lifetimes are far too brief to notice any change. In the crowded environment of a globular cluster, though, stars move noticeably faster through their celestial dance. These clusters serve as natural laboratories for astronomers who want to understand how stars age and evolve. Since all the stars in a cluster formed around the same time, billions of years ago, any differences between them come down to one main factor: their initial mass. It's like having a controlled experiment written across the cosmos. Scientists can observe stars at different stages of their lives, all within the same stellar family, and piece together the story of how stars are born, mature, and eventually fade away. The longevity of these clusters, some nearly as old as the universe itself, offers something quite profound for planetary science. Any worlds that exist in these environments have had the chance to evolve over truly vast stretches of time. We're talking about planetary systems that have endured not just the slow changes that come with stellar aging, but also the constant gravitational tugging and pulling from thousands of neighboring stars. The fact that planets can survive in such chaotic conditions tells us something important about the resilience of planetary systems. They're apparently robust enough to handle both the gradual evolution of their parent stars and the complex gravitational interactions that occur when you pack so many massive objects into a relatively small space. One of the most intriguing possibilities in these stellar cities is the existence of rogue planets. Sometimes when stars pass particularly close to each other, their gravitational fields can literally steal planets from neighboring systems. These orphaned worlds end up wandering through the cluster, no longer tied to any single star, but still held within the overall gravitational embrace of the cluster itself. Picture these lonely worlds drifting through space, illuminated only by the collective glow of distant suns. They would be cold, dark places, cut off from the warming radiation of a nearby star. Yet some of these wandering planets might still harbor interesting environments. If they managed to retain thick atmospheres or possessed significant internal heat sources, they could potentially maintain subsurface oceans or other hidden refuges for complexity to emerge. Studying such worlds directly would present enormous challenges, but their very existence expands our notion of where interesting planetary environments might be found. They represent a category of world that simply doesn't exist in quieter regions of the galaxy, like our own stellar neighborhood. The long-term evolution of globular clusters adds another layer to this cosmic story. Over billions of years, these stellar communities gradually lose members as gravitational interactions and tidal forces from our galaxy slowly pull stars away. Astronomers call this process evaporation, though it happens on timescales that make geological processes seem rapid by comparison. As clusters evolve and lose stars, their internal structure changes. The density decreases in some regions, which might actually make things more stable for any surviving planetary systems. Worlds that experienced frequent close encounters with neighboring stars in the cluster's youth might find themselves in increasingly peaceful environments as the eons pass. The immense age of these clusters brings a certain perspective to our thinking about permanence and change in the universe. Individual stars are born, live their lives, and die, sometimes in spectacular fashion. Planetary systems form, evolve, and may eventually be disrupted. But the clusters themselves persist for timescales that dwarf almost everything else we can observe. A planet orbiting a star in one of these ancient assemblages could have a history stretching back to when our galaxy was young and still forming. Such a world would have witnessed the slow transformation of its stellar neighborhood over billions of years, watching as the cluster's structure shifted and evolved around it. The orbit of such a planet would continue its predictable path while the surrounding population of stars gradually changed. Some stars would leave the cluster entirely, while others might migrate to different regions within it. The planet would serve as a silent witness to these vast transformations, though of course without any awareness of the cosmic drama unfolding around it. What strikes many scientists about these environments is how alien they seem compared to our own corner of the galaxy. Yet they operate according to exactly the same physical principles that govern our solar system. Gravity works the same way. Radiation behaves identically, and orbital mechanics follow the same mathematical relationships, whether you're in the sparse outskirts of a spiral arm or the crowded core of an ancient cluster. The differences we observe arise not from different physics, but from different initial conditions, different densities, and the effects of vastly different amounts of time. It's a reminder that the universe is both remarkably consistent in its fundamental rules and endlessly creative in the variety of environments those rules can produce. The discovery of planets in globular clusters has encouraged astronomers to search more systematically for additional worlds in these ancient environments. Each new detection helps refine our understanding of how common planets really are in such settings, and how planetary systems respond to prolonged exposure to complex gravitational fields. As our telescopes become more sensitive and our data analysis techniques grow more sophisticated, it seems likely that we'll find more of these cluster planets. Future discoveries might include smaller, rocky worlds that are much harder to detect with current methods, but could be even more interesting from the perspective of understanding planetary formation and evolution. When we consider the vast timescales involved, some of these planets might have existed for nearly the entire history of our galaxy. They formed when the Milky Way was young and have persisted through billions of years of gradual cosmic evolution. Such worlds, if they exist, would be among the most ancient planetary systems in the known universe. Contemplating these distant ancient environments offers a quietly humbling perspective on our place in the cosmos. Our solar system, for all its familiarity and importance to us, represents just one possible arrangement among countless others. The universe contains stellar neighborhoods and planetary environments that are profoundly different from anything we experience here, yet equally valid expressions of the same underlying physical principles that shape our own world. The universe operates on a timescale that dwarfs our human experience, and nowhere is this more apparent than when we consider planets that have existed for 10, 12, even 15 billion years. These ancient worlds have witnessed cosmic events we can barely imagine, and their very existence challenges our understanding of planetary evolution and survival. When a planet first forms, it's essentially a ball of molten rock and metal, radiating intense heat from the violent collisions that brought it into being. Radiating elements within its core continue to generate warmth, keeping the interior fluid and dynamic. But as millions of years turn into billions, this heat slowly leaks away into the cold vacuum of space. The cooling process transforms everything about how a planet behaves. Early in its life, a rocky world might experience constant volcanic eruptions, with lava flows reshaping the surface every few thousand years. Tectonic plates slide and collide with tremendous energy, building mountain ranges and opening deep ocean basins. The planet's surface remains young, constantly renewed by geological activity. But time changes this dramatic dance. As the interior cools, volcanic activity becomes less frequent, then rare, then eventually stops altogether. The crust grows thicker and more stable. Tectonic motion slows to a crawl, then ceases entirely. What was once a geologically violent world becomes quiet, almost serene, in its stillness. Mars offers us a glimpse of this process, though on a relatively small scale. Billions of years ago, Mars had active volcanoes, flowing rivers, and possibly a thick atmosphere. Today, it's a quiet world, where ancient impact craters remain perfectly preserved, unmarked by the geological processes that would have erased them on a younger, more active planet. An ancient rocky planet might be even more subdued than Mars. Its surface could be covered with countless impact craters, accumulated over billions of years of bombardment by asteroids and comets. Without plate tectonics to recycle the crust, or flowing water to erode the landscape, these scars remain as a permanent record of the planet's long journey through space. The mountains on such a world would have been worn down by incredibly slow processes. Temperature changes between day and night, bombardment by tiny micrometeorites, and the gradual breakdown of rock minerals would slowly soften the landscape. What might once have been jagged peaks could become gentle. Rolling hills, shaped more by patience than by violence. Atmospheres tell their own story of planetary aging. Young planets often have thick atmospheres rich with gases released by volcanic activity. But over billions of years, these protective blankets can slowly disappear. Light gases like hydrogen and helium escape into space, especially if the planet has weak gravity or lacks a strong magnetic field to protect them. The star's radiation plays a crucial role in this atmospheric erosion. High-energy particles break apart atmospheric molecules, changing their chemistry and allowing them to escape more easily. Some planets might lose their atmospheres entirely, leaving their surfaces exposed to the harsh environment of space. Venus and Mars show us two different paths of atmospheric evolution. Venus managed to keep its thick atmosphere, though it became a hellish greenhouse in the process. Mars lost most of its atmospheric envelope, leaving behind only a thin whisper of what it once had. Gas giant planets experience their own version of aging, though it's quite different from rocky worlds. When these massive planets first form, they're still glowing with heat from their creation. Jupiter, for instance, still radiates more energy than it receives from the Sun, a leftover warmth from its formation 4.5 billion years ago. But even gas giants cool down over time. They contract slightly as they lose heat, and their atmospheric patterns change. The swirling storms and colorful bands that make them so beautiful slowly shift and evolve. A gas giant billions of years older than Jupiter would still be massive and stable, but cooler and less luminous in infrared light. The stars these ancient planets orbit also age, and stellar evolution has profound effects on planetary environments. Our Sun has grown about 30% brighter since Earth formed, and this gradual increase in luminosity has significantly affected our planet's climate. Over billions of years, this brightening can evaporate oceans, melt ice caps, and completely alter atmospheric chemistry. Some stars undergo even more dramatic changes. Sun-like stars eventually swell into red giants, potentially engulfing their inner planets, or at least scorching them beyond recognition. More massive stars explode as supernovas, creating neutron stars or black holes and fundamentally changing the radiation environment for any surviving planets. The Methuselah planet, one of the oldest known worlds at nearly 13 billion years old, orbits in a system that has experienced these extreme changes. The original massive star exploded long ago, leaving behind a neutron star. Another star in the system evolved into a white dwarf. The planet now receives very different radiation than it did during its early history. If we could somehow watch such a planet over billions of years, the changes in its sky would be remarkable. Stars would slowly drift across the heavens as the entire star cluster moved and evolved. Some nearby stars would brighten and fade as they aged, while others would suddenly flare up and die, leaving behind faint remnants barely visible to any hypothetical observers. The accumulation of impact craters tells another story of planetary aging. While large asteroid and comet impacts become less frequent after the early chaotic period of planetary system formation, they never stop entirely. An ancient world's surface might preserve a record of impacts stretching back almost to the beginning of the solar system. These craters would overlap and intersect, creating complex patterns that chronicle billions of years of bombardment. Some craters would be so old, they'd be barely recognizable, worn down by eons of slow erosion. Others would be relatively fresh, sharp-edged reminders of more recent cosmic collisions. For icy worlds, different processes shape the surface over time. Sublimation and redeposition of ice gradually alter the landscape. Temperature variations cause the ice to evaporate in some places and condense in others. Radiation from space slowly changes the chemical composition of the surface layers. Some of the icy moons in our own solar system already show signs of these processes. Europa's surface appears to be constantly renewed by geological activity beneath its frozen shell. But on an ancient icy world, billions of years of these subtle changes could completely transform the surface texture and appearance. Magnetic fields also evolve with planetary age. These invisible shields are generated by the motion of electrically conducting fluid in a planet's interior. As the interior cools and solidifies, this motion slows or stops entirely, weakening the magnetic field. Earth's magnetic field has protected our atmosphere for billions of years, but it won't last forever. On a planet much older than Earth, the magnetic field might have already disappeared, leaving the atmosphere vulnerable to being stripped away by stellar winds and high-energy radiation. Even the color of ancient planets might differ from younger worlds. Chemical reactions driven by sunlight and cosmic radiation gradually alter surface minerals. On airless bodies, constant bombardment by tiny particles and cosmic rays slowly darkens the surface through a process called space weathering. The result is a surface that becomes more uniform and subdued over time. Bright, colorful minerals fade to darker, more neutral tones. The dramatic color contrasts visible on younger worlds give way to more muted, weathered appearances. When we consider all these processes together, ancient planets emerge as quieter, more subdued versions of their younger selves. They're shaped more by slow, patient change than by rapid transformation. They carry subtle signs of their immense age in their temperature, geology, atmosphere, and orbital environment. There's something profoundly moving about contemplating such ancient worlds. A planet that has existed for 12 billion years has been witness to cosmic events we can barely comprehend. It formed when the universe was less than 2 billion years old, when the first generation of stars was still shining, and heavy elements were much rarer than they are today. These worlds remind us that the universe has been evolving for far longer than our species has existed, and will continue long after we're gone. They're libraries of cosmic history, their surfaces and atmospheres preserving records of events that happened when the Milky Way was still young. Yet, despite their age, these planets are not static museums. They continue to orbit their stars, respond to gravitational influences, and participate in the ongoing evolution of their stellar systems. Age doesn't mean stillness, it means long participation in the endless dance of cosmic forces. The very existence of such ancient planets also tells us something important about planetary survival. These worlds have endured stellar evolution, cosmic bombardment, and billions of years of slow change. They've survived in environments that have transformed completely from their original conditions. This resilience suggests that planets, once formed, can persist through almost unimaginable spans of time. They adapt to changing conditions, whether it's the slow brightening of their star, the gradual loss of internal heat, or the evolution of their stellar neighborhood. In contemplating these ancient worlds, we're forced to expand our perspective beyond the relatively brief span of human history, or even Earth's history. We're reminded that our planet, at 4.5 billion years old, is actually middle-aged by cosmic standards. There are worlds out there that were already ancient, when our solar system was just a disk of dust and gas around the young sun. The challenge of identifying truly ancient worlds lies in their deceptive simplicity. When we observe a distant planet, we cannot simply look at it and declare its age with confidence. A world that has orbited its star for 12 billion years might appear nearly identical to one that formed just a few billion years ago, if they share similar mass and composition. The secrets of planetary age hide within subtle clues, waiting for careful detective work to reveal them. Astronomers must become cosmic archaeologists, reading the history written in starlight and chemical signatures. The host star becomes a timekeeper, its spectrum revealing the abundance of heavy elements that tell us about the galactic environment when it formed. Early in our galaxy's history, fewer heavy elements existed, because generations of stars had not yet lived and died to scatter these materials through space. A star poor in metals, as astronomers call elements heavier than hydrogen and helium, likely formed when the universe was much younger. The broader galactic context provides another layer of evidence. Ancient stellar clusters, those dense communities of stars that formed together billions of years ago, serve as time capsules. Planets discovered in these environments carry the age of their stellar neighborhoods, marking them as relics from an earlier cosmic epoch. As detection methods grow more sophisticated, we learn to interpret these subtle signs more effectively. Each observation teaches us something new about reading the cosmic calendar, about distinguishing the genuinely ancient from the merely old. The techniques continue to evolve, revealing planets that witnessed the early chapters of galactic history, but age alone tells us little about a world's capacity to nurture life. The passage of billions of years does not automatically render a planet hostile or welcoming. What matters far more are the fundamental requirements that make a world habitable in the first place. Temperature must allow for liquid water, or at least some form of solvent where chemical reactions can occur. The atmosphere needs stability, neither too thin to retain heat, nor so thick that it creates a runaway greenhouse effect. Consider what makes our own world so remarkably suited for life. Earth sits at just the right distance from the Sun, in what we call the habitable zone, where water remains liquid on the surface. Our atmosphere strikes a delicate balance, thick enough to trap some heat, but not so dense that it turns our planet into a furnace like Venus. The magnetic field generated by our planet's molten core deflects most of the charged particles streaming from the Sun, protecting our atmosphere from being slowly stripped away. Beneath our feet, geological processes constantly recycle elements essential for life. Plate tectonics carries carbon-rich rocks into the deep interior, while volcanic activity returns these materials to the surface and atmosphere. This grand recycling system helps regulate our planet's climate over geological timescales, maintaining conditions within ranges that life can tolerate. Yet none of these favorable conditions will last forever. Our Sun gradually grows brighter as it ages, and in roughly 1 billion years, this increasing luminosity will begin evaporating Earth's oceans. The surface will become far less hospitable, marking the beginning of the end of our planet's habitable phase. This inevitable change reminds us that habitable change, not a permanent state. For truly ancient worlds to remain habitable over immense timescales, they require different circumstances. Small, dim stars that burn their fuel slowly offer the best prospects for long-term habitability. Red dwarf stars can shine steadily for tens of billions of years, far longer than larger stars like our Sun. A planet orbiting such a star could potentially remain in the habitable zone for extraordinary periods, assuming other factors align favorably. Many ancient planets discovered in old stellar clusters indeed orbit these smaller, longer-lived stars. This fact alone increases the possibility that habitable conditions could persist far longer than they will on Earth. But ancient systems face their own unique challenges that younger planetary systems do not. The low metal content of early stellar generations creates complications for habitability. With fewer heavy elements available during planet formation, ancient worlds might lack the substantial rocky crusts, large iron cores, and strong magnetic fields that help maintain stable climates. Such planets might exist, but they could be smaller and less geologically active than Earth, potentially affecting their ability to regulate their environments over cosmic time. Atmospheric retention becomes increasingly difficult over billions of years. Several processes can slowly strip away a planet's air, including thermal escape where hot gas molecules gain enough energy to reach space, bombardment by stellar winds that knock atmospheric particles away, and chemical reactions driven by radiation that break apart atmospheric molecules. A strong magnetic field provides some protection, but as a planet's interior cools over time, this magnetic shield may weaken and eventually disappear entirely. An ancient planet might therefore have lost much of its original atmosphere eons ago, leaving behind a cold, airless world. Without an atmosphere to distribute heat and maintain pressure for liquid water, such a planet would struggle to support surface life as we understand it. However, habitability need not require Earth-like surface conditions. In our own solar system, moons like Europa and Enceladus likely harbor vast oceans beneath their icy surfaces. Tidal forces from their giant planet hosts generate heat within these moons, keeping their subsurface waters liquid despite receiving little warmth from the distant sun. These hidden oceans remain shielded from radiation and might stay stable for billions of years. Ancient planets could host similar environments. Even if a world's surface freezes and its atmosphere disappears, internal heat sources or tidal interactions might maintain liquid water in underground reservoirs. Such environments could support life far longer than surface conditions would allow, protected from the changing radiation environment as their host star evolves. Life in these hidden realms would not depend on sunlight for energy. Around hydrothermal vents on Earth's ocean floors, entire ecosystems thrive in perpetual darkness, drawing energy from chemical reactions rather than photosynthesis. Similar processes could sustain life in the subsurface oceans of ancient worlds for immense periods. The stability of planetary orbits also influences long-term habitability. A world's climate depends heavily on the regularity of its path around its star. Significant changes in orbital distance or axial tilt can trigger extreme climate shifts that challenge the survival of existing life forms. Ancient planetary systems that have maintained dynamically stable configurations for billions of years might offer more predictable conditions, at least in this crucial respect. Radiation environments present both challenges and opportunities for ancient worlds. In dense stellar clusters, stars crowd together more closely than in typical galactic neighborhoods. This proximity means that violent events like supernovae might have occurred nearby more frequently in the past, potentially sterilizing planetary surfaces or stripping away protective atmospheres with intense bursts of radiation. Yet these catastrophic events remain relatively rare, even over billions of years. And planets located in quieter regions of their clusters might avoid the worst effects. Paradoxically, the great age of these systems could actually favor habitability in some ways. The most massive short-lived stars that produce the most dangerous radiation have long since exhausted their fuel and disappeared. What remain are smaller, gentler stars that evolve slowly and emit less intense radiation. An ancient cluster today might be far calmer than it was during its turbulent youth. The question of biological evolution adds another fascinating dimension to ancient habitability. On Earth, simple life appeared relatively quickly after conditions became suitable, within roughly 1 billion years of our planet's formation. But complex, multicellular life required billions of additional years to develop and diversify into the forms we see today. A planet that has remained habitable for 10 billion years would have provided far more time for evolution to unfold, assuming life arose there initially. We do not yet understand how commonly life emerges even under favorable conditions, making this scenario highly speculative, but the possibility intrigues scientists and philosophers alike. Ancient habitable worlds could potentially host ecosystems far older and more complex than anything on Earth, simply because evolution would have had much more time to explore biological possibilities. Energy sources become critically important for life persisting over such vast timescales. Even if a planet loses its atmosphere or surface water, life might continue underground, sustained by geothermal energy from the planet's warm interior. On Earth, scientists have discovered microbes living kilometers beneath the surface, thriving in conditions once thought too extreme for any life form. These deep environments remain stable over long periods, isolated from surface changes and external radiation. An ancient planet with sufficient internal heat could support similar underground ecosystems for billions of years, even if its surface appears completely barren. Tidal heating offers another potential energy source for very old worlds. In systems where planets or moons experience strong gravitational interactions with nearby massive bodies, these tidal forces generate heat within the interior through constant flexing and stretching. This process can maintain liquid subsurface oceans and drive geological activity long after a world would otherwise have cooled into lifelessness. Some ancient planets might opportunities fight, creating unique habitability challenges and opportunities. During the earlier phases of stellar evolution, when the star swelled into a red giant before collapsing into a white dwarf, any planets would have faced intense radiation and heat that likely stripped away atmospheres and sterilized surfaces. However, theoretical studies suggest that habitable conditions might emerge again around white dwarfs if planets somehow migrate into the habitable zone after the star stabilizes in its compact final state. These scenarios remain largely theoretical, but they demonstrate that habitability is not limited to planets orbiting main sequence stars like our Sun. The universe might host many different types of habitable environments, some of which we have barely begun to imagine. The broader environment of ancient stellar populations also shapes the prospects for long-term habitability. In globular clusters, the gravitational influence of nearby stars can perturb the outer regions of planetary systems, potentially disturbing reservoirs of comets and asteroids. This disruption might increase the frequency of impacts on inner planets. While occasional impacts do not necessarily prove catastrophic for life, and may even deliver useful materials like water and organic compounds, frequent large impacts could pose significant challenges for maintaining stable biospheres over cosmic time. Nevertheless, the very survival of planetary systems in these dense stellar environments for billions of years suggests that catastrophic disruptions are not inevitable. Many systems appear to experience long periods of relative calm between major disturbances, providing windows of stability where life might take hold and flourish. Contemplating habitability over such immense timescales forces us to confront the temporary nature of even the most favorable conditions. Earth has maintained a habitable environment for billions of years, but this pleasant state will not continue indefinitely. Climate systems, stellar evolution, and geological processes all change with time, constantly shifting the boundaries of what we consider habitable. A planet's ability to support life represents a phase in its evolution, not a permanent characteristic. Ancient planets remind us that these habitable phases can persist far longer than we might initially expect, but they also emphasize that change remains inevitable. Mountains rise and fall, atmospheres evolve, stars grow brighter or dimmer, and the cosmic environment itself transforms as galaxies age and evolve. The search for potentially habitable worlds has traditionally focused on planets similar to Earth, orbiting stars similar to our Sun, but studying ancient planetary systems encourages a much broader perspective on where and how life might arise and persist. Habitability could manifest in many different forms, some of which stretch our current understanding and imagination. As telescopes become more powerful and our detection methods more sophisticated, astronomers may eventually study the atmospheres of very old planets directly. We might search for chemical signatures that could indicate ongoing biological activity, looking for the subtle imbalances in atmospheric composition that life tends to create. Such discoveries would revolutionize our understanding of life's prevalence and persistence throughout the universe. For now, the question of whether ancient planets can remain habitable over cosmic timescales remains tantalizingly open. The evidence suggests that at least some of them could maintain environments suitable for life under the right combination of circumstances, but we have much more to learn about the specific conditions required and how commonly they occur. Each new discovery adds another piece to this vast puzzle, gradually revealing the true scope of habitability in our ancient, ever-changing universe. The early Milky Way was a fundamentally different place than the galaxy we observe today. More than 12 billion years ago, when the universe itself was only a few billion years old, our galaxy contained vastly more cold gas, the essential fuel for star formation. This abundance of raw material meant that stars were being born at rates far exceeding what we see in modern times. Back then, the chemical makeup of space was remarkably simple. Hydrogen and helium dominated everything, while heavier elements remained scarce. This happened because fewer generations of stars had completed their life cycles. Each stellar death enriches the surrounding space with complex materials, but in those early epochs, this process was still in its infancy. The night sky of that ancient galaxy would have blazed with massive, brilliant stars. These stellar giants burned with incredible intensity, though their lives were necessarily brief. Their powerful radiation and stellar winds constantly stirred the gas around them, creating turbulent conditions throughout vast regions of space. When these massive stars eventually exploded as supernovas, they scattered heavier elements into the interstellar medium, beginning the slow process of cosmic enrichment. Star formation occurred primarily within enormous molecular clouds, where new suns ignited in great clusters. Sometimes hundreds or thousands of stars would form together in relatively small regions of space. The galaxy pulsed with this energetic activity, creating what astronomers call a more active phase of galactic evolution. Globular clusters, those dense, spherical collections of ancient stars, were already old even in this early period. Many formed during the very assembly of the Milky Way itself, possibly when smaller protogalactic fragments merged together. These clusters orbited the young galaxy much as they do today, though their paths and internal structures have shifted over billions of years. From inside such a cluster, the view would be extraordinary. Dense concentrations of nearby stars would fill the sky in every direction, creating what might feel like a self-contained stellar city. The broader galaxy beyond would appear as a faint, diffuse glow behind this crowded foreground of brilliant suns. The galactic disk was still taking its final shape during this period. Spiral arms, which many people think of as permanent structures, are actually temporary patterns created by density waves moving through the disk. These waves compress gas and trigger star formation, but the patterns themselves shift and evolve over cosmic time. The spiral arms we see today are not identical to those that existed billions of years ago. At the galaxy's center, the supermassive black hole now called Sagittarius A star had probably already grown to a significant portion of its current mass. However, it may have been more active in the past, occasionally drawing in gas and emitting powerful bursts of radiation across the galaxy. One of the most striking differences in the ancient Milky Way was simply the sheer abundance of available gas. Star formation gradually converts this raw material into stars and planets, and while gas continues flowing into the galaxy from intergalactic space, the overall supply slowly decreases as any galaxy ages. Billions of years ago, there was simply more fuel available for making new stars. This increased activity made the galaxy a considerably more energetic environment. Supernova explosions happened more frequently, and radiation from massive stars was more intense across many regions. For planetary systems trying to form in these conditions, the challenges were significant. Protoplanetary disks faced exposure to strong ultraviolet radiation, and nearby explosions could disturb or completely strip away their material. Yet somehow, some planetary systems managed to form and survive in these harsh conditions. Ancient planets like the famous Methuselah planet represent survivors from this early era, when the galaxy was still building up the heavy elements that make rocky worlds possible. The distribution of stars was also different billions of years ago. Over immense spans of time, stars migrate through the galaxy, their orbits shaped by gravitational interactions and the overall mass distribution of the galactic disk and halo. A star currently near our Sun may have formed in a completely different region and slowly moved to its present location. This process of radial migration means that the current arrangement of stars doesn't perfectly reflect where they originally formed. Ancient planets may have traveled through dramatically different galactic environments during their lifetimes, experiencing varying levels of radiation, stellar density, and chemical composition as they moved. The galactic halo, that vast spherical region surrounding the disk, contains many of the oldest stars and globular clusters. In earlier epochs, this halo was likely more active, filled with remnants of smaller galaxies that merged with the growing Milky Way. Evidence of these ancient mergers still exists today in streams of stars moving together through the halo, the scattered remains of dwarf galaxies torn apart by tidal forces. These galactic mergers were much more common in the past, and they contributed significantly to our galaxy's growth. When smaller galaxies merged with the Milky Way, they brought their own stars, gas, and possibly entire planetary systems. Some of the oldest planets that astronomers might discover in the future could have formed not in the Milky Way itself, but in completely different galactic environments that were later absorbed. The overall brightness of the galaxy may have been different during those distant times. With more active star formation and more massive stars, certain regions could have been dramatically brighter and more energetic than anything we see today. As star formation rates declined over billions of years and massive stars became less common, the galaxy gradually settled into its current, somewhat calmer state. Even the cosmic background radiation, that faint afterglow of the Big Bang, was slightly warmer and more intense billions of years ago, though still far too cold to influence planetary conditions directly. Its changing intensity serves as a reminder that the universe itself was younger and denser during the formation of the oldest known planets. For any hypothetical observers on ancient planets, the night sky would have appeared subtly different in other ways. Nearby galaxies would have seemed slightly closer, because the universe's expansion has been increasing distances between galaxies over time. The Andromeda Galaxy, which is gradually approaching the Milky Way now, would have been farther away billions of years ago and perhaps less prominent in ancient skies. The large-scale structure of the universe changes slowly, but given sufficient time, those changes become noticeable. Ancient planets have existed long enough to witness, in a purely physical sense, the gradual shifting of galaxies across cosmic distances. One of the most important differences in the early galaxy was the scarcity of elements like iron, silicon, and oxygen. This meant that rocky planets were probably less common than they are today, and those that did manage to form may have been smaller or compositionally very different from Earth. Gas giants, which depend primarily on hydrogen and helium, may have been relatively more frequent among the earliest planetary systems. As successive generations of stars lived, died, and enriched the interstellar medium, conditions for forming complex rocky worlds gradually improved by the time our solar system formed. Roughly 4.5 billion years ago, the galaxy had already undergone billions of years of chemical evolution, creating a much richer environment for planet formation. The gradual thinning of star-forming gas in certain galactic regions represents another major change over cosmic time. While new stars continue forming today, the overall rate has declined compared to earlier epochs. The Milky Way remains an active galaxy, but it's no longer in the most vigorous phase of its star-forming history. For ancient planets, this evolution means their surroundings may have become considerably quieter over time. Regions that once blazed with bright, short-lived stars and frequent supernovas may now be populated mainly by older, more stable stellar populations. This vast progression creates a profound sense of continuity, a reminder that today's galaxy represents only a single moment in an ongoing process that has been unfolding for billions of years and will continue for billions more. When astronomers study the oldest known planets, they're not just examining individual worlds, they're glimpsing actual relics of an earlier Milky Way, objects that formed when our galaxy was still young and have somehow persisted through all the dramatic changes since then. The human mind struggles with truly vast numbers. When we hear about billions of years, our brains often just file these away as labels, like calling something very old without grasping what that actually means. But behind these astronomical ages lies a story that connects us to the deepest rhythms of existence itself. Our universe has been expanding and evolving for roughly 13.8 billion years. This figure comes from multiple independent measurements, each telling the same story. Scientists measure how fast space itself stretches. They study the faint afterglow of creation still visible in every direction, and they examine the oldest stars we can find. All these methods point to the same conclusion, giving us confidence in this almost incomprehensible time span. Now imagine a planet that formed 12 billion years ago. This world came into being when our universe was barely 2 billion years old, still young and wild compared to today. Back then, galaxies were still assembling themselves from smaller pieces, like cosmic construction projects that had just begun. Heavy elements, the building blocks of rocky planets, were far more scarce than they are now. The Milky Way itself was a different place entirely. Star formation followed different patterns, and the chemical mix available for making new worlds was much simpler. The first long-lived stars were just settling into stable orbits within growing galactic structures. It was an era of cosmic use when the fundamental architecture of our galaxy was still taking shape. To put this in perspective, our Earth formed about 4.5 billion years ago. This makes our world less than 1/3 the age of the universe itself. Life appeared on Earth relatively quickly, perhaps within just a few 100 million years of the planet's formation. But complex life, the kind we see around us today, took billions of additional years to develop. Humans have existed as a species for only a few 100,000 years. Our recorded history spans just a few millennia. If we compressed the entire history of the universe into a single year, Earth would form in early September. The first complex life would appear in December, and all of human civilization would occupy only the final seconds before midnight on New Year's Eve. a planet that formed 12 billion years ago, would appear near the very beginning of January in this cosmic calendar. It would have witnessed the formation of countless other worlds, including our entire solar system, as mere recent events in its impossibly long existence. Stars themselves live and die on different timescales that help us understand these vast ages. Massive stars, despite being several times heavier than our Sun, burn through their fuel quickly and may explode as supernovas after just a few million years. Our Sun will live for about 10 billion years in its current stable phase, steadily converting hydrogen into helium in its core. But the smaller stars, called red dwarfs, can live for tens or even hundreds of billions of years. This means they'll outlast our universe's current age many times over. Some of the oldest planets in our galaxy may still be orbiting stars that haven't even reached middle age yet. From such a star's perspective, 12 billion years isn't an ending, but merely one long chapter in an even longer story. Planets don't have fixed lifetimes the way stars do. In principle, a world can persist indefinitely, as long as nothing destroys it through collision, stellar consumption, or gravitational ejection. Some planets may continue orbiting long after their stars have evolved into white dwarfs, those dense stellar remnants that glow dimly for billions or trillions of years. This makes planets among the most enduring structures in the universe. They can outlast not just individual stars, but entire phases of galactic evolution. They become witnesses to cosmic change on scales we can barely imagine. Our galaxy began forming stars more than 13 billion years ago, shortly after the first galaxies appeared. The earliest stars were massive and short-lived, but later generations included smaller, longer-lived stars capable of hosting planetary systems for immense spans of time. Globular clusters serve as time capsules from these early epochs. Many are more than 12 billion years old, their stars remaining gravitationally bound for nearly the galaxy's entire history. Any planets within such clusters would share that incredible longevity. The time scale of galactic motion adds another layer to this story. Our Sun takes about 230 million years to complete one orbit around the Milky Way's center. Since forming, it has made roughly 20 such journeys. A 12 billion-year-old planet may have completed more than 50 galactic orbits, traveling hundreds of thousands of light-years through space, while remaining bound to its star. These long journeys expose planetary systems to changing cosmic neighborhoods. They might pass through spiral arms rich with gas and active star formation, then move into quieter regions, then encounter new clouds and stellar clusters. Over billions of years, a planet's surroundings can transform repeatedly, even while the world itself maintains a stable orbit. The future adds even more perspective to these timescales. Our universe will continue expanding for trillions of years ahead. Star formation will gradually decline as available gas gets used up or dispersed. Many stars will burn out, leaving behind white dwarfs, neutron stars, and black holes. Galaxies will slowly reshape themselves through gravitational interactions and mergers. In that distant future, surviving planets may continue their orbits around faint, stellar remnants, illuminated only by the dim glow of white dwarfs or distant starlight. Compared to these future timescales, even 12 billion years represents just an early chapter in the cosmos's long story. On Earth, our oldest rocks are about 4 billion years old, but plate tectonics constantly recycles our crust, erasing much of the earlier geological record. Worlds without active geology can preserve surface features far older than anything found on our planet, offering more direct records of ancient events. Meteorites provide windows into deep time that complement planetary studies. Some meteorites formed in our solar system's earliest days and have remained largely unchanged for more than 4 billion years. They're fragments of the original material from which planets assembled, preserved in space's cold vacuum. Ancient planets, especially those with little geological activity, may preserve similar records on much larger scales. They become libraries of cosmic history, their surfaces and compositions holding clues to conditions that existed when the universe was young. Thinking about cosmic time can influence how we understand change itself. Many astronomical processes unfold gradually. Stars brighten slowly over millions of years. Orbits evolve subtly through gravitational interactions. Galaxies shift and merge over timescales that dwarf human comprehension. These changes remain invisible within human lifetimes. But over immense spans, they transform the universe completely. Ancient planets serve as witnesses to these slow transformations, having orbited through multiple phases of stellar and galactic evolution. The age of elements themselves adds another dimension to this story. The atoms that make up planets were forged in stars that lived and died before those worlds formed. Some atoms in Earth's crust are older than our Sun, created in supernovas billions of years earlier. Planets are assembled from material carrying history that stretches almost back to the universe's beginning. When astronomers measure planetary and stellar ages, they're not just determining formation dates, but tracing matter's history through cycles of stellar birth, death, and renewal. Discoveries of very old planets have surprised scientists who once believed planet formation was a relatively recent development, requiring multiple stellar generations to produce sufficient heavy elements. Finding ancient worlds shows this process began much earlier than expected. This means planetary systems may have existed throughout most of our galaxy's history. It expands our understanding of how long environments suitable for planets, and possibly life, may have existed. The story of worlds isn't confined to recent billions of years, but extends almost to the Milky Way's beginning. Reflecting on these immense timescales can feel both humbling and oddly comforting. It reminds us that the universe operates on scales far beyond our daily concerns. The slow motion of stars and galaxies, the gradual evolution of planets, and the steady passage of billions of years create a sense of continuity that transcends our brief individual experiences. Ancient planets embody this continuity perfectly. They remind us that the processes shaping our cosmos have operated for vast stretches of time and will continue long into futures we cannot imagine. In their patient orbits around ancient stars, they carry forward the memory of a universe that was young when they formed, connecting the deepest past to whatever cosmic stories remain unwritten. When we peer into the depths of space, we encounter something quite remarkable. Planets that have been spinning through the cosmos for 10, 12, even 15 billion years. These ancient worlds offer us a window, a glimpse into processes that unfold over timescales our minds can barely grasp. Think about it for a moment. We live on a planet that's roughly 4.5 billion years old. That seems ancient to us, but in cosmic terms, Earth is practically middle-aged. These older worlds have already experienced the full journey that Earth is still traveling. What becomes immediately clear when studying these ancient planets is that nothing stays the same forever. Change happens everywhere, on every world, but it happens slowly. So slowly that if you could somehow watch it unfold, most of the time you wouldn't notice anything happening at all. The interiors of planets cool down over billions of years. Their atmospheres transform completely. Mountain ranges rise and fall, oceans appear and disappear, and the very stars they orbit grow brighter or dimmer with age. It's like watching the universe's longest, slowest movie. Our own sun provides a perfect example of this gradual change. Right now it's about halfway through what astronomers call its main sequence lifetime. That's the stable period when a star fuses hydrogen in its core. But here's something fascinating. The sun has been getting brighter, steadily, throughout Earth's entire history. When Earth first formed, our sun was dimmer than it is today. The climate back then was completely different. In another billion years or so, the sun will have grown bright enough to make Earth too hot for liquid water on the surface. The oceans will boil away. Our planet won't disappear, but it will become something entirely different. This might sound alarming, but ancient planets teach us that this kind of transformation is perfectly normal. Habitability isn't permanent, it's more like a phase. Sometimes it's a very long phase, lasting billions of years, but it's still just one chapter in a much longer story. What's remarkable, though, is how resilient planetary systems can be. We've discovered planets that have survived for over 10 billion years, sometimes in regions of space that are far more chaotic than our quiet neighborhood. Their orbits remain stable despite experiencing events that seem like they should destroy everything. Some planets have survived the death of their star, others have endured close encounters with neighboring stars, or lived through their galaxy colliding with another galaxy. They adapt, they persist, they find new ways to continue existing. This gives us hope about the future of our own solar system. When the Sun eventually runs out of hydrogen fuel, it will expand into what we call a red giant. This will happen in about 5 billion years. Mercury and Venus will almost certainly be swallowed up completely. Earth's fate is less certain, that the surface will become uninhabitable long before the Sun reaches its maximum size. But here's the interesting part. The outer planets, Jupiter, Saturn, Uranus, Neptune, they'll probably survive. After the Sun sheds its outer layers, it will shrink down into a white dwarf star. These outer planets will continue orbiting this white dwarf remnant. The solar system won't be gone. It will be transformed into something quieter, colder, but still there. Ancient planetary systems show us exactly how these transformations play out. They reveal how long the remnants of solar systems can persist, continuing their dance around stellar corpses for billions of additional years. There's also something profound about initial conditions. Where a planet forms, how massive it becomes, what kind of star it orbits, how crowded its neighborhood is, all of these factors determine its long-term fate. Earth has been remarkably fortunate in many ways. We have a relatively stable orbit. We have a large moon that keeps our planet's tilt steady, preventing wild climate swings. We're located in a comparatively calm region of the Milky Way, far from the chaotic center, where stars are packed more densely together. Not every planet gets such favorable conditions. Ancient systems show us a wide variety of outcomes. Some remain stable for billions of years. Others experience constant chaos. Some get reshaped completely by gravitational interactions with their neighbors. The evolution of atmospheres over these vast timescales is particularly fascinating. Earth's early atmosphere contained almost no oxygen. Oxygen only accumulated after tiny organisms learned to photosynthesize, fundamentally changing the chemistry of our air and making complex life possible. But atmospheric evolution doesn't stop there. Volcanic activity continues to pump gases into the air. Biological processes keep altering the chemical balance. The oceans interact with the atmosphere in complex ways. Over billions of years, these processes can completely transform what a planet's atmosphere looks like. Some ancient planets may have lost their atmospheres entirely, stripped away by stellar winds or cosmic events. Others might have developed thick, dense envelopes of gas that bear no resemblance to what they started with. Each case teaches us something about the range of possibilities for atmospheric evolution. The cooling of planetary interiors is another process that ancient worlds illuminate beautifully. Right now, Earth's internal heat drives plate tectonics. It powers volcanic activity. It generates our magnetic field. These processes help regulate our climate and protect us from harmful radiation. But this internal heat isn't infinite. Over very long timescales, planets cool down. Geological activity slows. Magnetic fields weaken and sometimes disappear entirely. We can see this process in an early stage on Mars. Once geologically active, possibly warmer, Mars cooled more quickly than Earth because it's smaller. As Mars cooled, its magnetic field faded. Its atmosphere thinned out. Much of its surface water was lost to space. Earth will cool more slowly because of its larger size, but given enough time, similar changes are inevitable. Ancient planets proved that this long-term cooling isn't just theoretical speculation. It's a natural, unavoidable part of how planets evolve over cosmic time. This brings us to something profound about time itself. On Earth, life required billions of years to evolve from simple microorganisms to complex creatures, and eventually to beings capable of contemplating the universe. Ancient planets, if they remained habitable for even longer periods, might have provided even more time for biological evolution to unfold. This perspective changes how we think about searching for life beyond Earth. Instead of only looking at planets similar in age to our own, we might want to pay special attention to much older worlds, where life, if it arose at all, would have had vast stretches of time to develop into forms we can barely imagine. These ancient worlds also offer insight into the future of our galaxy itself. The Milky Way continues to evolve over billions of years. Star formation will gradually decline as available gas gets consumed. In about 4 to 5 billion years, our galaxy will merge with the nearby Andromeda galaxy, creating a single, larger galactic system. Our solar system will be carried along during this merger, eventually finding itself orbiting within an entirely new galactic structure. From a planet's perspective, this merger will unfold slowly, over hundreds of millions of years. The night sky will change gradually, with new patterns of stars appearing as the galaxies approach and combine. Ancient planets that existed during earlier mergers in our galaxy's history may have already experienced similar transformations. They've watched their night sky change, seen new constellations appear, adapted to new galactic environments. This long view also reveals how temporary many features of planetary systems really are. Rings around planets gradually dissipate, asteroid belts change as objects collide or get ejected from the system. Comets are slowly depleted or redirected onto new paths. Even moons drift slowly outward or inward over time due to tidal forces. Our own moon, for example, is moving away from Earth at a rate of about 4 centimeters per year. Earth's rotation is gradually slowing down as a result. These changes are tiny on human timescales, but over billions of years they become dramatic. Ancient planets remind us that these slow processes never stop. They continue steadily, patiently reshaping the future in ways that may not be obvious in the present moment. What's reassuring, though, is the persistence of simple physical laws. Gravity works the same way now as it did 10 billion years ago. Thermodynamics hasn't changed. Orbital mechanics follows the same rules. The ancient planets we observe today formed under the same basic principles that govern our solar system. This continuity allows astronomers to use present-day observations to understand events that occurred long before Earth existed. We can read the history written in ancient starlight and planetary motions. In a broader sense, studying these ancient worlds encourages a kind of patience in thinking about the future. Human societies naturally focus on timescales of years, decades, maybe centuries. Astronomy deals routinely with millions and billions of years. Seeing the universe through that lens shifts perspective completely. Change is constant, but it's often gradual. Stability, when it occurs, can last far longer than we might expect. Crisis and catastrophe, while real, play out against a backdrop of cosmic patience. The existence of planets older than Earth also underscores something humbling and beautiful. Our planet is part of an ongoing story, not the final chapter. There were worlds before Earth formed, spinning through space, hosting their own geological dramas, perhaps even their own forms of life. There will be worlds long after Earth has changed beyond recognition. New planets forming around young stars, beginning their own billion-year journeys of evolution and transformation. Reflecting on this can shift our perspective in profound ways. It places our planet, our species, our moment in time within a much larger context. One where creation, transformation, and persistence are continuous processes unfolding on scales that dwarf human experience, but somehow make that experience more meaningful, not less. The atoms floating in the air around you right now, they weren't always here on Earth. They came from somewhere else entirely, forged inside stars that burned out billions of years ago. The carbon in your body, the oxygen you're breathing, the iron in your blood, all of it was created in stellar furnaces that existed long before our solar system even began to form. When we think about the oldest planets in our galaxy, we're really thinking about worlds that have been witnesses to almost everything. These ancient spheres have been around since the universe was still relatively young, still figuring out how to make the heavy elements that rocky planets need. The very first planets that formed, they had to work with what was available at the time. Mostly hydrogen and helium, with just tiny traces of heavier stuff. Those early stellar generations, they lived fast and died dramatically. They exploded as supernovas, scattering their newly created elements into space like cosmic seeds. Then the next generation of stars formed from this enriched material, and they could finally start building planets that looked more like the rocky worlds we know today. There's something almost meditative about how slowly the universe operates. Stars don't rush through their life cycles. They burn steadily for millions, sometimes billions of years. Planets don't hurry through their orbits. They follow the same gravitational paths over and over again, year after year, eon after eon. This patient rhythm exists completely outside our human sense of urgency. The oldest planet we've actually discovered so far is a world that's been around for about 12.5 billion years. That means it formed when the universe was only about 1 billion years old, practically a cosmic infant. This ancient world has been circling its star since before our own Milky Way galaxy had finished settling into its current spiral shape. Think about what this planet has witnessed during its incredibly long existence. It was already ancient when the first complex molecules began forming on Earth. It had already completed billions of orbits when life first appeared in our oceans. While dinosaurs roamed our planet, this distant world was already older than our Earth is today. The star this ancient planet orbits, it's what astronomers call a subdwarf. These stars are small and dim, burning their fuel so slowly that they can potentially shine for trillions of years. That's far longer than the current age of the entire universe. So while our own sun will eventually expand into a red giant and then fade away, these tiny stars will keep burning long after our solar system has become just a memory. What strikes many people as beautiful about this is the sheer endurance involved. No effort, no struggle, just the simple persistence of physical laws playing out across unimaginable stretches of time. Gravity keeps the planet in its orbit, nuclear fusion keeps the star shining, and time just flows onward like a river that never stops moving. We can only guess at what the surface of such an ancient world might be like. It probably doesn't have the dynamic geology we see on Earth. No plate tectonics constantly reshaping the landscape. Instead, it might be a quiet place, scarred by billions of years of meteor impacts, but otherwise largely unchanged. The same mountains and craters that formed early in its history could still be there, patient monuments to deep time. The radiation from its dim red star would cast everything in a perpetual twilight, neither day nor night as we understand them. Seasons, if they existed at all, might be subtle affairs, slight changes in the angle of that red light across landscapes that have remained essentially frozen for geological ages. When astronomers search for these ancient worlds, they're really looking backward through time. Light from distant stars takes years, sometimes centuries, to reach our telescopes. So when we observe these far-off systems, we're seeing them not as they are now, but as they were when that light first began its journey toward us. The techniques used to find planets around other stars, they're remarkably clever. Most of the time, astronomers can't actually see the planets directly. Instead, they watch for tiny dips in starlight that happen when a planet passes in front of its star from our perspective, or they look for the subtle wobble that a planet's gravity creates in its star's motion. Each detection is like solving a cosmic puzzle. The size of the light dip tells us how big the planet is. The time between dips reveals how long its year lasts. The amount of wobble in the star's motion gives us clues about the planet's mass. Slowly, carefully, we build up a picture of worlds we'll probably never visit. The galaxy is full of planetary systems we haven't discovered yet. Some of them might be even older than the ancient worlds we've already found. There could be planets out there that formed when the universe was even younger, circling stars so faint we can barely detect them, or drifting through interstellar space after being ejected from their original systems billions of years ago. This vastness, this sense that there's always more to discover, it can be oddly comforting. The universe is patient enough to wait for us to find these things. There's no cosmic deadline, no rush to figure everything out immediately. The ancient planets will keep orbiting their stars whether we discover them this year or in decades to come. Sometimes it helps to imagine yourself standing on one of these ancient worlds, looking up at an alien sky. The constellations would be completely unfamiliar, patterns of stars that exist nowhere in Earth's sky, but the same physical laws that govern our world would apply there too. Gravity would still pull things downward, light would still travel at the same speed. Time would still flow at its steady pace. The deep history of the universe, it's not really separate from our daily lives. It's the foundation that everything else rests on. The slow formation of heavy elements in stellar cores, the gradual accumulation of dust and gas into planetary systems, the patient evolution of galaxies over cosmic time, all of this led eventually to the existence of our world, our civilization, this very moment. There's something humbling about realizing that we're part of this much larger story. Human history, all of recorded civilization, it's just the tiniest sliver at the very end of a timeline that stretches back billions of years. Yet it's also empowering to know that we've developed the tools and knowledge to peer back into that deep history, to understand our cosmic origins. The light from those ancient stars, it's still traveling through space right now. Some of it might reach Earth tonight, carrying information about worlds and systems that formed when the universe was young. Patient photons that have been journeying across the galaxy for geological ages, finally arriving here, where we have telescopes and instruments capable of reading their cosmic stories. The universe operates on a timescale that dwarfs human experience, and this creates something remarkable, a sense that possibility itself is infinite. When we think about the sheer scale of cosmic time, billions upon billions of years stretching ahead, it becomes clear that whatever happens in our brief moment, the larger story continues. Stars that seem permanent to us are actually temporary, burning through their fuel over millions of centuries. But even as they fade, new ones ignite in distant nurseries of gas and dust. This vastness carries a peculiar comfort. While our individual concerns feel urgent and all-consuming, the cosmos maintains its patient rhythm. Planets that formed when the universe was young still trace their elliptical paths around ancient suns, some of these worlds perhaps harboring processes we can barely imagine. The dance of gravity that holds these systems together operates according to the same fundamental principles that govern the air moving in and out of our lungs, the circulation that carries oxygen through our bloodstream. There's something profound in this connection between the grand and the intimate. The carbon in our bodies was forged inside dying stars, scattered into space when those massive suns exploded, then slowly incorporated into new worlds, new possibilities. Every breath contains atoms that once belonged to distant stellar cores, now participating in the quiet chemistry of life on this small planet. Globular clusters, those dense spheres of ancient stars, contain some of the oldest objects in our galaxy. Hundreds of thousands of suns packed together so tightly that if we lived on a planet there, the night sky would blaze with thousands of brilliant points, bright enough to read by. These clusters have been drifting through space since shortly after the Milky Way formed, witnesses to cosmic history spanning nearly the entire age of the universe. Our galaxy itself changes, but slowly, almost imperceptibly. Over hundreds of millions of years, spiral arms shift and reorganize. Stars migrate from their birthplaces. New regions light up with star formation, while others fade into quiet middle age. The supermassive black hole at the galactic center occasionally flares as material falls into it, sending ripples of energy across vast distances. Meanwhile, other galaxies move through the darkness beyond our own, each one containing billions of stars, countless worlds we will never see. Some of these island universes are approaching us, others receding, all part of a larger pattern of motion that began with the expansion of space itself. In the deepest surveys our telescopes can make, we find galaxies so distant that their light has traveled for most of the age of the cosmos to reach us. The physical laws that orchestrate this grand choreography are the same ones that keep our hearts beating steadily, that allow neurons to fire in precise sequences, that enable the simple miracle of consciousness to emerge from ordinary matter. Gravity pulls planets in their orbits and blood through our veins. Electromagnetic forces hold atoms together in stellar cores. and in the proteins that make life possible. This continuity suggests something about the nature of existence itself, that the boundary between self and universe might be less absolute than we typically imagine. We are not separate observers looking out at a foreign cosmos, but rather temporary arrangements of cosmic material that have become aware of their own origins. The iron in our blood was forged in stellar explosions. The calcium in our bones crystallized in ancient supernovae. The water in our cells condensed from primordial hydrogen, and oxygen in the cold reaches between stars. Even as we rest, as consciousness fades towards sleep, the larger processes continue their unhurried work. Distant worlds maintain their patient orbits, binary stars exchange material. In complex spiraling dances, nebulae slowly collapse under their own gravity to birth new generations of suns. Time moves differently out there, measured not in heartbeats or breaths, but in the slow progression of stellar evolution, the gradual drift of continents on far-off planets, the million-year cycles of galactic rotation. In this context, the urgency that often characterizes human experience finds a different perspective. The universe has been conducting its grand experiment for nearly 14 billion years, and current models suggest it will continue for trillions more. Long after our sun has exhausted its fuel and become a slowly cooling ember, within that immense span, every moment of awareness, every instance of curiosity about the cosmos, represents something genuinely remarkable. The fact that ordinary matter can organize itself into forms capable of contemplating their own existence seems like one of the universe's most extraordinary achievements. Somewhere in the complexity of neural networks, in the flow of chemical signals between synapses, consciousness emerges, bringing with it the capacity for wonder, for questions about meaning and origin and destiny.